Okay. I think we should start soon. Looks like we're live. So let's give it about 30 seconds so that people can join. After that, I'll introduce today's speaker, and then we'll get started. Okay, maybe it's time to get started. Looks like we have a good critical mass. Okay, welcome everyone for our next Safari Live seminar today. Today we have Minesh Patel, who's a PhD student at Safari, who's going to talk about essentially his PhD thesis research. Minesh started in Safari as a PhD student at CMU, and then he moved to ETH, and he's been around for about 6 years now. And the good news is he's defending his PhD thesis next week. And this is going to be a good overview of all the work he has done during his PhD as first author, at least the work that will go into his PhD thesis. Minesh is going to be talking about enabling effective error mitigation and memory chips that use on-die error correcting codes. And this is going to be an overview of multiple works. I think 5 works Minesh has done. 4 of them are published, and 2 of them have received best paper awards, one at DSN in 2019 and the other one at Micro in 2020. And 1 work is coming up at Micro 2021 next week, I think, or in 2 weeks, that Minesh is also going to present. Okay, I think with that, I'll leave it to Minesh. And feel free to ask questions online on YouTube. We will handle them as they come in. Minesh, please go ahead. Thanks.
All right, perfect. Thanks, Oner. So thanks for the introduction. So hello, everyone. And as Oner said, I'm Minesh, and today I'm going to introduce the work I've been doing in my PhD. So here's the overall structure of this seminar today, and I'll start off with a short introduction and motivation for the work in common. So let's start with a look at a conventional computing system. So here we have a processor that operates on data and main memory that stores data. In this talk, we'll mostly focus on DRAM, or dynamic random access memory, which is widely used throughout modern systems. So these 2 components are typically connected with a standardized interface, and this allows interoperability between processors and DRAM chips from different manufacturers. And this interface also provides a separation of concerns between the 2 parties, allowing each of these groups to focus on solving their own design challenges. Now, a key DRAM challenge in modern systems is that DRAM is fundamentally susceptible to various errors, and these errors can cause data loss or system failure if they're simply ignored. To make matters worse, DRAM manufacturers' primary goal is to increase storage density, but this exacerbates errors over time. And this both results in increased costs for manufacturers and consumers, and also limits systems' overall potential for growth. And so the solution to address these issues is to use error mitigation techniques, which fix errors before they can impact the system. And so an error mitigation mechanism typically takes in erroneous data, here illustrated with the yellow thunderbolt, and outputs the corrected data. Most recently, DRAM manufacturers have begun using on-die error correction, or on-die ECC. And here we picture an erroneous DRAM module that's susceptible to errors. So on-die ECC operates entirely within the DRAM, and it's proprietary and fully self-contained. Therefore, it operates in a way that's completely invisible to the processor. In doing so, on-die ECC hides the most common errors that occur from the processor. Now, on-die ECC is a popular solution for several reasons. First, it is simple and low cost. Second, it preserves trade secrets that DRAM manufacturers do not want to reveal. For example, how exactly these errors are being addressed. And third, it is convenient for many commodity systems because it just works. However, on-die ECC has several downsides. First, it can only correct a limited number of errors. And this is because addressing all possible errors within the DRAM itself is very expensive. And second, as a result of this partial correction, on-die ECC makes designing other error mitigations complicated. So these downsides lead me into the key problem that we addressed throughout this work, which I can state as follows. So on-die ECC negatively impacts system design and test efforts. And this is because on-die ECC takes predictable and or well-understood errors that result from physical processes and passes them through an unknown filtration from this partial correction, effectively resulting in unpredictable, obfuscated errors that are difficult to understand or reason about. So let's take a look at some of the parties who are impacted by this obfuscation. First, error mitigation designers are forced to make limiting assumptions, for example, to assume worst-case behavior that then lead to inefficient designs. Second, third-party testers find it hard to test and debug observed errors because on-die ECC conceals the underlying root cause for these errors. And third, research scientists who perform experimental studies to better understand DRAM technology characteristics find that their studies are polluted by artifacts from on-die ECC. And so to address this problem, this leads me into my research statement, which is that we can use new memory testing techniques to recover error characteristics that our on-die ECC obfuscates. And in particular, these new memory testing techniques exploit the interactions between on-die ECC and the statistical characteristics of memory errors. And in doing so, these techniques enable scientists and engineers to make informed decisions towards building robust systems. Okay, so that concludes the introduction and motivation, and now I will move on to discuss our core contributions. So here, I've put these core contributions together in the context of the parts of the system they address. And so this simple diagram here illustrates a DRAM chip that uses on-die ECC. Our first core contribution, Reaper, focuses on the rightmost side of this figure within the data store itself. And this work seeks to understand the basic DRAM error characteristics themselves. Our second contribution is Ein, which focuses on the interface between on-die ECC and the data store, where the error characteristics are hidden, but they're unaffected by on-die ECC. And this work uses statistical inference to recover those characteristics, despite not being able to directly observe them. Our third contribution is Beer, and this focuses on the on-die ECC logic itself. This work essentially develops a technique to determine how the on-die ECC logic works, which describes exactly how on-die ECC performs this obfuscation. Our fourth contribution is HARP, which focuses on how errors appear to the processor. And this work develops a technique to efficiently identify those bits that are at risk of error, even though on-die ECC complicates this process. And our final contribution is a set of recommendations that we have based on the work that we've done throughout the other contributions. And this work targets the interface between the processor and the memory and argues that transparency of reliability characteristics is essential for consumers to understand and adapt commodity DRAM chips to the needs of their particular systems. So I'll start by discussing our first contribution, Reaper, in more detail. So I think I'll pause for a moment in case there's a question. Okay, I'll move on. So I'll pause, I think, at strategic points throughout the works, just in case questions arise. Okay, so I'll start off with the high-level summary of this work. So the high-level motivation we have is that DRAM refresh is a major impediment to technology scaling, especially in terms of energy consumption. And the specific problem that we focus on is that DRAM retention failure profiling is difficult. And this is because of a number of effects that cause cell retention times to change dynamically. And current profiling methods are either unreliable or they're just too slow. And so our goals in this work are twofold. First, we would like to thoroughly characterize the trade-off space surrounding retention failure profiling. And second, we want to use what we learn to develop a fast and reliable profiling mechanism. And to this end, we make two main contributions. First, we perform the first detailed characterization of 368 LPDDR4 DRAM chips. And second, we use what we learned from our error characterization study to propose reach profiling, which profiles at a longer refresh interval and or a higher temperature relative to the target operating conditions where cells are more likely to fail. And so through our evaluations, we find that reach profiling increases profiling performance by an average of 2.5x and enables longer refresh intervals that previously were unreasonable due to the profiling overhead. And so I'll start off by giving a little background on DRAM refresh. So DRAM encodes data in fundamentally leaky capacitors. And so here's a simplified diagram of a DRAM cell. Here, data is encoded in the capacitor as either charged or uncharged, and the access transistor is used to read from or write to the cell. Now, there are a number of charge leakage paths by which charge can enter or exit the capacitor. And the important thing to note is that because of these leakage paths, the stored data in the capacitor can be corrupted if too much charge leaks. And this is the same as saying as if the capacitor voltage degrades too far. And so here we have a simplified diagram of the capacitor voltage over time. And we see that the voltage decreases in an exponential decay curve. We define a voltage V min, after which we can no longer tell what data was originally stored in the cell. Therefore, as long as the voltage remains above V min, we consider this to be a retention success. However, as soon as the voltage drops below V min, we consider this to be a retention failure and the data can potentially be corrupted. Now we define a term called retention time, which defines how long the cell can safely hold its value. Now we have to keep in mind that DRAM is much more than just a single cell. In fact, DRAM can be composed of hundreds of billions of cells. And as a specific example, a 8 gigabyte DRAM contains in excess of 64 billion cells. And we have to make sure that none of these cells experience a retention failure. So to this end, we use a process called DRAM refresh. And DRAM refresh periodically restores the charge in all DRAM cells. For current devices, every cell is refreshed approximately every 64 or 32 milliseconds. And this is referred to as the refresh interval. And this has significant impact on system performance and energy consumption. So here's some data from our evaluations to illustrate this. The y-axis here shows the average system performance overhead incurred for DRAM chips of different sizes along the x-axis. And we see that this performance penalty is significant, especially for larger DRAM chips, which have more cells that need refreshing, especially for chips, approximately 64 gigabits and larger that we may expect to see in the future. Now, we don't actually have to refresh so often. And in fact, most cells can handle a longer refresh interval. So here are some empirical data that we gathered from a representative DRAM device at a temperature of 45 degrees centigrade. The y-axis here shows the number of cells that fail at different x-axis values, which represent different refresh intervals that we operate the chip at. Note that the y-axis here is actually a log scale. So here we see that for even a modest increase in the refresh interval past the default of 64 milliseconds, we only have a small number of failures. Now, prior works have proposed many ways to mitigate retention failures in order to allow safe operation at longer refresh intervals. However, all of these works need a way to reliably identify the failures that occur. And this essentially means that we need a fast and reliable profiling mechanism to identify the set of retention failures that occur. So now I'll talk about some of the challenges surrounding retention failure profiling. Okay, so here's a diagram that shows an idealized DRAM refresh operation. So we have a number of cells shown in green and a refresh counter that counts down the time until the next refresh operation occurs. So as the refresh operations continue, we see that the charge in each cell decreases over time, but it's restored every 64 milliseconds by the refresh operation. Now, this is an idealized picture because all the cells shown here have identical retention times, and that means every cell is refreshed right before it fails. In this case, there would be no need for profiling at all because we're already operating at the ideal refresh interval. Unfortunately, real DRAM cells are not so ideal, and they exhibit significant variations in retention time, as we showed earlier. So let's take a look at some of the sources of this variation. First, cell retention times depend heavily on process variation, and they change dynamically with effects such as changing voltage and temperature. Second, data pattern dependence effects mean that the retention time of a cell actually depends on the value programmed both into the cell itself and its neighboring values. For example, a cell containing, for example, a DRAM that's programmed with all ones would have a different set of retention failures than if the DRAM contained all zeros. And the third effect that we need to talk about is variable retention time. And this effect means that the retention time of cells changes randomly, and more importantly, it changes unpredictably. And this occurs due to a combination of various different circuit level effects and leakage mechanisms. And prior work has shown that VRT effects essentially mean that ECC is necessary in order to sustain operation at longer refresh intervals. So given these sources of variation, let's take a look at a more realistic picture of DRAM refresh. Here we have cells with varying retention times, and the green cells here are shown with long retention times and the red cells with short retention times. And we see that the red cells that have short retention times come much close to failure than do the green cells with long retention times. And this essentially means that the cells with short retention times, essentially the red and potentially the yellow cells, require a short refresh interval. And the cells with a longer retention time, can handle a longer refresh interval. So now let's take a look at what happens when we use a longer refresh interval across all of the different cells. So here we operate at an extended refresh interval of 128 milliseconds, which is twice the default of 64 milliseconds. And when we do so, we see that the red cells with short retention times actually end up failing. And that means that we have 3 retention failures in this example. And so the problem we want to solve is how can we quickly and reliably determine the set of failing cells at a given increased refresh interval t. Okay, so I'll move on to the next section, which is to talk about current approaches to retention failure profiling, or at least let's say current at the time of this work. So the first approach that we consider is called ECC scrubbing. And so the key idea to ECC scrubbing is to leverage error correcting codes by periodically accessing all of the different ECC words in the device in order to continuously detect any new failures that occur. And so the pros of this approach are that it's very simple because we're simply doing a bunch of read accesses to DRAM. And that means it's also relatively low overhead because DRAM is available for normal operations in between and during scrubs. However, this approach can be unreliable because it does not account for changes in data patterns that can occur between scrub operations. And this could potentially change cell retention times and essentially make the profiler miss retention failures in between scrub operations. The second solution that we consider is what we call brute force profiling. And the key idea here is that for n different data patterns over m different testing rounds, we first write data to the DRAM device, we wait for the desired profiling refresh interval, and third, we check for any errors that occurred. And so the pros of this approach is that it's rather reliable because it finds a higher percentage of all possible failures by using many different data patterns, many different profiling rounds, and explicitly inducing worst case conditions. However, we find that with this approach, it's rather slow because many different testing rounds are required to provide high reliability. And therefore, it can be high overhead because DRAM is actually unavailable for normal operation during the profiling process. And so our goals in this work are twofold. First, we want to study the trade-offs surrounding retention failure profiling. And second, we want to use what we learned from the study to develop a fast and reliable profiling mechanism. Okay, so now I'll talk a bit about our experimental characterization study of LPDDR4 DRAM chips. So in terms of our experimental infrastructure, we test 368 state-of-the-art LPDDR4 DRAM chips, where each chip is 4 gigabits in size, and we have chips from across 3 major DRAM manufacturers. We conduct all of our testing in a thermally controlled testing chamber, which has an ambient temperature of between 40 to 55 degrees centigrade with a tolerance of 0.25 degrees centigrade. And in order to ensure consistency of this temperature, the DRAM temperature is always held at 15 degrees centigrade above the ambient temperature using a localized heating source. Okay, so here are the studies that we performed using our infrastructure. And we find that the first 3 studies here, temperature, data pattern dependence, and retention time distributions, show results rather similar to those shown by prior works for older generation devices, namely DDR3 DRAM. Therefore, in this presentation, I'm going to focus on number 4 and 5, variable retention time and individual cell characterization, which show new results that help motivate our mechanism. So here's some data that we collected from a representative chip at a fixed refresh interval of 2048 milliseconds. Here we're showing the number of new failing cells that were discovered on the y-axis across continuous profiling through 6 days of testing. And we find that new failing cells actually continue to appear over time. And we attribute these cells to variable retention time effects, which mean that cells can randomly change retention times at any point in time and potentially require more testing to discover. And this result essentially shows that the set of failing cells changes over time. And we conclude that error correcting codes are actually necessary to provide online profiling in order to manage all of these new failing cells that occur. In another study, we analyzed the failure probabilities of individual cells. And so this diagram shows the probability of read failure for a single cell over different refresh intervals shown on the x-axis. And so this green curve shows an idealized cell which never fails at a refresh interval below 3 seconds, but always fails at a refresh interval above 3 seconds. And so we can say that this cell has a retention time of 3 seconds. However, we find that a realistic cell looks more like the curve shown in blue, which follows a normal distribution, which has its mean at 3 seconds. Now, note that this means even below 3 seconds, the cell can potentially fail with some non-zero probability. Now here we show data from a real chip. And so this is collected by testing how often a given cell fails out of 16 trials. And for example, for the highlighted point shown, the cell was observed to fail 9 times out of 16 trials. at the given refresh interval on the x-axis. And so we now show 8 different cells taken from the same chip, and it's a little easier to think about these if we apply their normal distribution fits. So now suppose that we're interested in operating at a refresh interval of 1.7 seconds, shown by this bar, this vertical line essentially. And we'll find that there are 6 cells that fail with a non-negligible probability of failure at this refresh interval. However, the bottom 2 cells will be relatively hard to find because they have a low probability of failure at this refresh interval. Now, if we instead profile for errors at an increased refresh interval, say 1.9 seconds, we'll find that the same cells will be much easier to find because they have a higher probability of failure. However, as a consequence, we will also identify some other cells that fail at the profiling conditions, but not the operating conditions, and we refer to these as false positives. And so we repeat the same analysis for temperature variation along the x-axis, and we find that any cell is more likely to fail at a longer refresh interval or at a higher temperature. And so this leads me into the key idea of reach profiling, which I will talk about next. Okay, so the key idea of reach profiling is to profile not at the desired operating conditions, but rather at a longer refresh interval and or a higher temperature, where cells are more likely to fail. And so the pros of this approach are that it's faster and more reliable because we are profiling for failures where they're most likely to occur. However, we will also identify false positives, which fall under which fail under the profiling conditions, but do not fail under the operating conditions that we want to operate at. And so here's a graphic to represent the choices that we have in reach profiling. So we identify a set of target conditions at which we want to operate, and we have a choice as to what conditions we can profile at. For example, if we profile at an increased temperature refresh interval, we can profile faster and more reliably, but we incur false positives. In contrast, if we profile at a lower temperature or a lower refresh interval, we'll profile more slowly and potentially less reliably, but we'll identify fewer false positives, if any. And so this essentially represents that there's a complex trade-off space surrounding profiling. And so as it stands, reach profiling, as I described, is a very general methodology. And so in order to turn it into a concrete implementation, we have 3 key questions that we want to answer. First, what are the desirable profiling conditions that we want to operate at? Second, how often should the system perform profiling? And third, what information does the profiler actually need in order to conduct profiling? And so to figure all of this out, we identified 3 key metrics that we can use to characterize any retention failure profiling mechanism. The first is runtime, which defines how long profiling takes. The second is coverage, which describes the proportion of all cells that are observed to fail by the profiler. And third, the metric is false positives, which represents the number of cells that are essentially observed to fail during profiling, but don't fail during normal operation. And so in our studies, we explore how these metrics change under various different profiling conditions. So now moving back to the 3 questions we originally asked, the first is, what are desirable profiling conditions? And so we find that there are similar trends across both chips and vendors. And we find that on average, in order to maintain 99% coverage of failures, we can obtain a 2.5x speedup by profiling at 250 milliseconds above the desired operating conditions. And this comes at a cost of a 50% false positive rate. And we can actually push the speedup to over 3.5x by profiling 500 milliseconds higher than the desired operating conditions, but this comes at an increasing false positive rate. Now, we have many more examples of the trade-off space and more detail about it in the paper. And so if you're interested, we prefer you to take a look at it. The second question is, how often should we actually perform profiling? And so in order to answer this question, we make estimates using a probabilistic model. And we find that we can use our empirical data to make estimates here, and the details of the actual model that we use are in the paper. And as an example result, we find that we need to reprofile every 2.3 days for the conditions shown on the slide, or a 2 GB ECC enabled DRAM profiling at the described conditions to achieve 99% coverage. The third question that we ask is, what information do we actually need to know in order to conduct profiling? And so to answer this, the first thing we need to know is the cost of handling the identified failures. And this very much depends on the particular mitigation mechanism that we're using, because that determines how many errors we can actually mitigate and thus how aggressively we can profile. Second, we need some sort of empirical per chip characterization data in order to reliably make estimates of the different profiling parameters for a given chip. And this helps us understand a good place in the trade-off space to actually profile at. And we provide more detail about exactly what this entails in our paper. So finally, I'll move on to our end-to-end evaluations. Okay. So we evaluate Reaper which is our simple implementation of reach profiling. And so Reaper makes a number of pessimistic assumptions. First, it assumes that the entire system pauses during profiling, and so no useful work gets done. Right? This means that the profiler has some sort of firmware that executes the profiling routine, and it has exclusive access to DRAM. And so no other application can access DRAM while profiling occurs. And furthermore, we assume that Reaper can only manipulate the refresh interval and not temperature. So to describe our evaluation methodology, we use a simulator called Ramulator to evaluate performance and DRAM power to evaluate DRAM energy. And we model a typical 4-core system that uses 4 channels of LPDDR4 DRAM. And we measure performance and energy across 20 random 4-core benchmark mixes that are drawn from the spec CPU 2006 benchmark suite. Okay, so here's a plot of our simulated end-to-end performance gain for enabling operation at different refresh intervals. So here, the different refresh intervals are shown along the x-axis. And for each point, the 3 different box plots show the distribution of benchmark performance for brute force profiling, Reaper, and the ideal profiling mechanism that incurs no profiling overhead from left to right, respectively. So first, we observe that for short refresh intervals where we reprofile rarely, the profiling overhead is not very significant, and both profiling mechanisms come close to the ideal mechanism. However, the story is very different at longer refresh intervals where we have to reprofile very often. And here, the profiling overhead is very significant and actually begins to degrade system performance. Now, we see that at moderate refresh intervals of 1024 and 1280 milliseconds, Reaper visibly outperforms brute force profiling because it is able to maintain more of the ideal profiler's benefit than brute force profiling is able to do. Overall, we find that Reaper enables a best case 16.3% system performance improvement and a 36.4% DRAM power reduction, which we show in our paper. And qualitatively, Reaper enables longer refresh intervals, which are unreasonable using brute force profiling. So there's a lot of other analyses in the paper that I couldn't get into here in this talk. And if you're interested, we encourage you to please go ahead and take a look. So this concludes my coverage of the first contribution. And so I'll pause for a minute to take any questions that might exist. Okay, so I will now move on.
Maybe I should ask one question related to this, since this is clearly DRAM retention times are getting worse, and this sort of techniques are going to be even more important into the future. If you go to the result, I'll ask a question about the result, and maybe I'll ask questions about the mechanism also. But if you look into the result over here, at least the performance results show that if you can get, at least for these workloads, if you can get the refresh interval to 512 milliseconds, the performance benefit kind of saturates, right?
Right. Yeah, that's correct. At that point, you could say that you have diminishing returns for continuing to increase the refresh interval further, even for the ideal mechanism, right? And very much so for the profilers that incur performance cost. Okay, sure. Yeah, I mean that makes sense, of course, but it's good to know that in a sense, right? Does the curve look similar for energy as well? Right. Yeah, we observed that the curve does look similar. I don't believe I have a picture of this here, but yeah, the energy impact is relatively smaller when you look at this from an overall system perspective, because the energy required for profiling operations is a relatively small component of all the energy consumed throughout the system. But if we focus on the DRAM subsystem specifically, yes, the curve very much does look similar to what we're observing here, where you do save some energy by reducing unnecessary DRAM refresh operations. But as you profile too much, you start introducing more energy consumption back. And so there is, again, a sort of sweet spot around this similar point. Okay, makes sense, yeah. One more question related to this. What is the baseline refresh interval in this case? Here, we're using a baseline refresh interval of 64 milliseconds. Okay. Yes. So as things, as the baseline refresh interval becomes smaller, the improvements will also increase, I assume, right? Right. Yeah, so I think that warrants further analysis because while what you said is correct, potentially there will also be significantly more errors by increasing the refresh interval. And so those two will interplay in a way that potentially the ideal, or I mean, I don't want to say ideal, but the best trade-off for this curve will move to a different point, potentially even lower, depending on the benefits versus the costs.
Yeah, sure, that makes sense. I think it may be good to reanalyze this at this point in time, because this work was done about 5 years ago, right? It was published in 2017, but it was mostly completed in 2016, if I recall correctly.
Yes, that's correct. Yes.
And certainly refresh has not become better over time in real DRAM devices. Okay. I have one more question on the mechanism, because you mentioned this complex trade-off space of profiling. If you go to those, I think that slide where you show 3 metrics that you're really trying to optimize.
Okay. So this one here?
Yeah, this one. Yeah, maybe it's good to understand this a little bit, because it's probably difficult to optimize all of the 3 metrics at the same time, right?
Right.
And your evaluations assume some particular point in the space of this optimization for these 3 metrics. So the question is, how much can you do better if you optimize the profiling?
Yeah, I mean, that's a very good question. I think this also relates to your earlier point where, as I guess with more modern DRAM devices, the error mechanisms themselves are sort of shifting a bit, right? So we might see more of these single bit unpredictable VRT errors these days. And so in order to capture those, you might actually be forced to sacrifice on some of these metrics, right? So to achieve better coverage of a significant number of VRT bits, you might need to profile more aggressively at higher refresh intervals, but this will incur more false positives just by nature of what you're doing. And so I think it's hard to say whether or essentially how the trade-off space evolves for different DRAM devices. Because these trade-offs are very inherent in the profiling process itself. And you're right in that at some level, whatever decision you make, whether you choose a set of profiling conditions that you believe gives a desirable trade-off for the specific mitigation mechanism that you're using, maybe if false positives are very expensive, you put more emphasis on that metric. Or perhaps if they're not such a big deal, you put much more emphasis on coverage and so forth. So I guess what I'm trying to say is that I think it very much depends on the system you're targeting and your goals as a system designer. And looking at this from a purely analysis of failures perspective, what we can say is that there is very much a trade-off between these metrics, and there's no one point that just wins in all 3. Does that answer what you're saying?
Yeah, I think so. I mean, there's no perfect answer to this, I think, because this is a complex trade-off space, and it also involves not just performance and energy, but also the overhead of profiling, as well as the overhead that you expose to the mitigation mechanism, right? Especially with false positives, for example, right?
Right.
Yeah. I wonder if there's an easy way of exploring the space, but yeah, maybe that's out of the scope of this work.
Yeah, I think we haven't looked into that too much ourselves, but I think it goes along with the themes of this concept of reactive profiling, right? Potentially, if we could have a profiler that doesn't cost so much to run, maybe it's potentially less effective, but we can run it often and have some sort of feedback from it to determine how the system is evolving or which point we prefer. We potentially could get a much better analysis of the space, just throughout runtime even. It's a pretty open problem, I think.
Yeah, I agree. Yeah, and potentially, I think maybe machine learning-based techniques could be used here, because it's a difficult problem, I think, for humans, in my opinion. Maybe humans can guide. Okay, I think there's one question on YouTube. Maybe I'll let Hassan or Geraldo phrase the question, and maybe I'll think of other questions in the meantime.
Thanks, Soner. Yeah, we have one question from YouTube. The question is, first, thanks for the seminar. And it asks, in contrast to the refresh interval, have you characterized the variation of cells failures probabilities with other metrics, as for example, VGD values or number of cells in one row column, or etc.? So have you considered other methods, Minesh, other than refresh?
Okay. So I feel like I understood two sort of pieces here. So the first, I think, yeah. So with respect to other sort of independent variables that we can control, so VDD, I think, is one such independent variable. Our testing infrastructure did not allow us control over that, and so I think the easy answer is no. We did not explore the effect of changing the voltage. For other, I guess, for the other part of the question, which is perhaps looking at cells at a different granularity, right, like a row or a column or some substructure. I think we looked at that to some extent in our analysis in the paper. For example, the error rates that we observe for across different rows, right? That's, I think, a pretty natural thing to look at because that's how we perform refresh operations currently at row granularity. But I think both we and a lot of other works have looked at that. And for example, some of the works that mitigate retention failures operate at row granularity by manipulating these refresh operations. And many of them conduct their own analysis of the same thing. And so we didn't observe anything surprising in our results here. And as I was saying, it's sort of similar to observations made in the past with older devices, such as some, the types of devices some of these studies use. So I think, yeah, we did sort of look at that, but we didn't observe anything too surprising.
Okay, thanks, Minesh. And this is the only question for now from YouTube.
Perfect. Yes. Yeah.
Maybe I should mention that related to voltage, Kevin Chang in his PhD thesis and his Sigmetrics 2017 paper, he did the characterization of the effect of changing the voltage on errors induced in modern DRAM chips at that time. So I would recommend people to look at it if they're interested in voltage-related studies. So maybe we can move on.
Okay, sounds perfect. Yeah, thank you, everyone. And yeah, if you have more questions or follow-up questions, please feel free to ask, and we can lead into a discussion. Okay, so I will continue on with the second contribution here, which is Ein.
So Minesh, before we go to Ein, we just got a new question related to Reaper. I guess would be pertinent to answer it now on YouTube. Okay. And it's quite simple. So it's how to decide false positive cells.
Sorry, what do you mean by how to decide?
I guess is how to figure out if you get a false positive cell or not by doing your profiling.
I see. Yeah. So I think I'll just move to that slide real quick to help clarify. So yeah. So I think as I understand the question, it's saying that as we're profiling, we'll observe a set of failures, but we don't really know whether those are true failures or they are false positives. I think that's so that's how I'll interpret the question. And I think the question is absolutely correct. The profiler does not have a way to distinguish between those unless that it actually wants to go repeat profiling at some other conditions and then compare the set of failures, but that's unlikely to happen. And so this is why we refer to them as false positives, because the profiler cannot draw the distinction and it simply has to treat them as other potentially erroneous bits that the mitigation mechanism needs to manage. I think that's really all there is to it, and further analysis would be required for the profiler to differentiate.
Makes sense. Thanks, Minesh.
Okay, perfect. Yeah. I'll move on, and hopefully that clarifies. All right. So yeah. So I will start off with a high-level summary of this work. So our motivation in this work is that experimentally studying DRAM error mechanisms can provide a lot of insights for improving performance, energy, reliability, security, so forth. And the specific problem that we observe is that on-die ECC makes studying errors very difficult. And this is because it distorts the true error distributions that are occurring in the physical cells using unstandardized invisible ECC functions. And the post-correction errors that we then observe lack the insights that we're trying to find from the pre-correction errors. And so our goal in this work is to recover the pre-correction information that's been masked by on-die ECC. And so to this end, we have two key contributions. First, we introduce error inference, or Ein, which is the statistical inference methodology that infers the ECC scheme used for on-die ECC. And in an example, this means the type of ECC used, the word length, its correction capability, and so forth. And Ein also infers the pre-correction error characteristics beneath the on-die ECC mechanism, and in particular, the error rate. and EIN works without any hardware intrusion or insight into the ECC mechanism. Our second contribution is EIN-SIM, which is an open source tool for applying EIN to real DRAM devices. And we have this as an open source tool available on GitHub at the link shown on the slide. We also provide an experimental demonstration of EIN using 314 real LPDDR4 DRAM devices. And we demonstrate that EIN is able to infer the on-die ECC scheme and the pre-correction error characteristics within these chips. So I'll start out by first giving some background on error characterization and on-die ECC. So the first question is, what exactly is DRAM error characterization? So we describe it as the process of studying how DRAM behaves when we deliberately induce bit flips. And so we might study things like operating timings across different values, error mechanisms and how they scale across different technologies, interactions between the CPU and DRAM, and even environmental effects such as temperature and voltage. And our hope is that by studying these, we can gain some sort of understanding about the DRAM device and exploitable insights that we can use to improve the system. So the next question is, how do we characterize DRAM? And so we typically have some sort of testing routine, such as we saw with the profiling mechanisms when in the previous set of slides. So this testing routine is input to a tester, which interfaces with the DRAM device. And by executing this testing routine, we obtain some sort of error distribution. And this might be spatial distribution of errors across the address space, temporal distributions of how errors vary over time, variation between different cells, or even comparisons between different devices. And these are all examples of error characterization studies that we might perform. And so the third question is, why do we want to study DRAM errors? And this is because errors provide insight into how a DRAM device actually works. And this is because error mechanisms are based on physical phenomena that are occurring at the circuit level within the device. And patterns within the errors can indicate opportunities for improvements. And so our hope is that we obtain some sort of characterization-driven insights that we can then use to improve performance, reliability, energy, security, and so forth. Okay, so let's take a look at some examples of different types of DRAM devices. So the first DRAM we consider is one without ECC, and this is sort of a standard DRAM device, which interfaces with the tester and directly communicates data back and forth. The second type of DRAM uses what's called as rank level ECC, or it's your typical server style DRAM. And here we have ECC logic within the tester itself, and the interface communicates raw data between the tester and the DRAM chips. And the third type of DRAM uses what's called on-die ECC, or integrated ECC. And here, ECC logic is built into the DRAM chips themselves, and it's invisible to the tester. And so the communication back and forth involves the tester sending data, but the DRAM sends corrected data back. And so in the first case, with no ECC, the raw data is exchanged unmodified. In the second type of DRAM device, the same is the case because the tester can simply bypass its ECC logic and communicate directly with the DRAM. However, in the third case, the on-die ECC modifies the raw data in a way that's outside of the tester's control. And unfortunately, the on-die ECC scheme cannot be bypassed. It's unknown to the tester and it's proprietary, and it's completely invisible to the tester. And so let's take a look at how ECC complicates the error characterization process. So in this example, let's suppose that we have some data that we're writing to a DRAM chip. And so here, let's say we have 3 different DRAM chips that use 3 different ECC schemes. And so we write this data, which first goes through ECC encoders within each of the different DRAM chips. And so the encoded data is then written to the physical cells. Now, note that this data is different between the different chips because they use different encoders. And for sake of example, let's say that errors occur in the exact same bit positions within the 3 different chips. Now, after ECC decoding, which let's say uses a single error correcting code, the tester will observe some data that it reads from the device. And so we see that this data is actually different across the 3 devices, even though the errors occurred in the exact same bit positions. So in the first device, we have a single error. In the second device, we have no errors at all. And in the third device, we have 2 errors. And so this example shows that observed errors can actually change depending on the ECC scheme, even though the errors occurring in the physical device are not changing. And so naturally, this makes error characterization difficult because we start off with some sort of pre-correction error distribution. And this distribution is based on some sort of physical DRAM error mechanism that's potentially well understood. And when we pass this through 3 different unknown ECC schemes, we end up with 3 different post-ECC error distributions that potentially look very different from each other. And these distributions are ECC scheme specific, and the original influence of the error mechanism is potentially lost. And so this causes 2 key problems for the characterization study. First, it prevents us from comparing error characteristics between devices. And second, it obfuscates the well-studied error distributions that we are expecting from the physical device. So let's take a look at an example of an error characterization study that we might conduct and how on-ECC interferes with it. So in this example, we're going to walk through a technology scaling study. And so the goal of this study is to look at how errors evolve across different technology generations. So here I show a cartoon graph where along the x-axis, we show different technology generations, V0 through V4. And on the y-axis, we show some sort of testing parameter value. So you can pretend this is temperature or voltage or some other parameter that we're testing in the study. So here, let's say we get some experimental data for device V0. And what this box plot here shows is the distribution of all bit errors within the device. And so we see that these errors fall within the range of y equals 0.4 to 0.8. Now, let's say we repeat the study for technology generations V1 and V2, and we observe some sort of error distribution. And so based on this, we can extrapolate some trend here, and we can say that this is consistent with some physical phenomenon, right? So let's say in this example, this is consistent with what we expect from process technology scaling. Now, when we go ahead and study devices V3 and V4, we might observe that their distributions actually look very different, and they diverge from this trend that we're expecting. And so we see this sort of kink that we don't expect to see. And so it might turn out that this is an ECC artifact, because what we're observing here are actually post-ECC error distributions. And using a methodology such as EIN, which we're proposing in this work, if we can recover the pre-correction error distributions, we can actually see that they might follow the distribution that we're expecting. And so our goal in this work is to recover these pre-correction error characteristics that on-ECC obfuscates. Okay, so now I'm going to move into talking about the mechanism that we propose, which is EIN. So EIN is based on the key observation that DRAM error mechanisms have predictable characteristics that are intrinsic to the DRAM technology. So for example, we talk about data retention errors, which we previously discussed a little bit in the context of Reaper. So these occur because DRAM encodes data in leaky capacitors, and these leakage rates vary due to process variation, and this requires us to perform periodic refresh operations. Now, by disabling refresh deliberately, we can induce data retention errors. And these data retention errors are well studied and they're very fundamental to DRAM technology because they relate to how DRAM encodes the data. Now, because of all these studies that have happened in the past, we know that these data retention errors exhibit predictable statistical characteristics. For example, when manipulating the refresh interval, we can expect an exponential bit error rate with respect to temperature. And we can expect that the errors themselves follow a sort of uniform random spatial distribution because the errors occur independently from one another. Now, we can make use of these characteristics to infer some information. So let's take a look at how we do that. So what we can do is we can exploit these error characteristics to infer the ECC scheme. And the benefits of this approach are that it works for any DRAM device that's susceptible to this error mechanism, and it's independent of any particular device or manufacturer. And in particular, it's independent of the on-ECC mechanism. So here I illustrate a typical device that uses on-ECC, and we're going to quickly define some terms to formalize this approach a little bit. So let's say the CPU, when it does a write operation, it writes a data word to the DRAM device. And this data word passes through the ECC encoder to be encoded as a code word. And the code word is what's actually physically stored into the data store. Now let's say that some errors occur within the data store, for example, data retention errors. Now when the CPU performs a read operation, it reads out what we refer to as code word prime. And here the prime refers to the potential presence of errors within the code word. Right? And so this code word prime is then decoded by the ECC decoder, and a data word prime is returned to the CPU. Now we observe several things from this system. First, the transformation from data word to data word prime is observable by the CPU because it's directly interfacing with these quantities. Second, the transformation from code word to code word prime is not observable to the CPU, but it's predictable based on these error characteristics that we already understand. And so using this correspondence between the observable and the predictable errors, the entire transformation along the path from data word to data word prime is potentially inferable. And so this leads us to EIN's key idea, which is to use these predictable error characteristics to infer both the ECC scheme and the pre-correction error rate. Okay, so let's talk about how we go about this inference in a little more formal manner. So what we want to know is that we want to know what is the most likely ECC scheme that's used in a device given a particular experiment that we run. And so the experiment might yield values such as error rates or what have you. So we can describe this probabilistically as the probability of S given X, where S is a particular ECC scheme, and X is an experiment that we ran, right? So for example, an error distribution or some inputs and outputs from the experiment. And so what we want is that we want to find the argmax of this expression over the quantity S, which will give us the most likely ECC scheme. And so it's difficult for us to evaluate this directly because we can't easily answer what the probability of a given scheme is. And so we invert this quantity using Bayes' theorem. And so we express this as the probability of X given S times the probability of S. And so this is a much more tractable expression because this probability of X given S represents the likelihood, which simply asks, are these results reasonable given a particular ECC scheme? Right? So the ECC scheme here is not an unknown, it's something that's given. And so the prior here just represents how likely is S. And so in our analysis, if we don't prefer a particular ECC scheme, we can just assume it's a constant value. And so this essentially describes a process known as maximum a posteriori estimation or map estimation. And we provide a more rigorous derivation of this in the paper, including the full optimization objective function that we deal with for this argmax expression. And we also extend this to infer not only the ECC scheme, but also characteristics of the pre-correction error distribution, which we represent here with this variable theta. So now map, essentially we can use this map estimation to define ein as a 4-step process. So the first step to this process is to define the experimental inputs, which is essentially the data patterns that we're going to test with and the error mechanism we're going to deal with. For example, we've been talking about data retention errors, so it could be as simple as that, a fixed data pattern with data retention errors. The second step is to identify candidate ECC schemes that we believe might be used in the device. And so we can obtain these through publications, for example. We can look at these circuit level papers that describe schemes that have been used in past devices, and we can study which schemes might potentially be used going forward and add those to the candidate set of schemes. The third step is to run experiments on the devices that we have using the experimental inputs we defined in step 1. And the fourth step is to perform the map estimation over the schemes that we identified in step 2. And so the output of this map estimation will be the most likely ECC scheme used in the device. Okay, so let's take a look at how this looks in practice. So we put this together to create this 4-step ein process. And the first step, again, is to choose the experimental setup that we're using. The second step here is to simulate suspected ECC schemes with the experimental setup in step 1. And we do this because it's our way of evaluating the probabilistic expression, because it gets very complicated with different ECC schemes and different error rates. And so we actually evaluate this using Monte Carlo simulation. And we'll soon talk about einsim, which is our tool for performing the simulation. The third step is to run the real chip experiments with the unknown ECC scheme. And so that's simply the experimental studies that we perform. And fourth, we look at the difference between 2 and 3 to perform inference. And here we measure the per scheme likelihoods for each of the schemes we simulated in step 2. Right? And so based on this analysis, we'll observe the highest likelihood scheme, which essentially is the most likely ECC scheme used in our device. And so to facilitate this process, again, we use simulation. And so I'll describe the simulator a little bit. So we call the simulator einsim, and einsim evaluates this map estimation using Monte Carlo simulation. And so einsim essentially simulates the life of a data word throughout a real experiment, right? So writing a data pattern, inducing errors, and reading the data back out. And we have configuration knobs to replicate the experimental setup across a variety of different experiments. And so we believe that einsim is flexible and extensible so that it can apply to a wide variety of different DRAM devices, error mechanisms, and ECC schemes, and so forth. And we encourage you to examine this for yourself, as it's an open source C++ and Python project available on GitHub. And we also provide the experimental data sets that we used in the paper at the GitHub link. And so again, we encourage you to give it a try. And if you're interested in these problems, maybe this tool is useful for your purposes. So finally, I will move on to our demonstration using LPDDR4 DRAM devices. So, okay, sorry, just briefly pausing in case any questions come up. But yeah, so I'll start off by describing our experimental methodology. And so similar to the previous paper, we experimentally test LPDDR4 DRAM devices. And here we have 232 devices with on-die ECC coming from one major manufacturer who was using on-die ECC at the time of this work, and 82 devices without on-die ECC, which come from across all 3 major manufacturers. We conduct all of our testing in a thermally controlled testing chamber, again, similar to the methodology of the previous work. And here we have precise control over all of the commands that we issue to DRAM. So for example, enabling or disabling self and auto refresh, control over all the CAS commands such as read and write and so forth. And so now I'll describe our experimental design a little bit. So our goal in this experiment is to infer which ECC scheme is used in the real LPDDR4 devices that use on-die ECC. And so here we have a set of testing parameters what we use in experiment and what we use in simulation that sort of describes the experiment. And so I'll go through these parameters. So the first is word size. And so in our experiments, we assume 256-bit words. Now, it's important to note that this actually works even if the experimental word size does not match the real word size of the on-die ECC, because we'll observe that regardless of this, the simulation experiments show that the most likely ECC scheme with the experimental word size used is still the same as if we had used the word size that's actually used by the ECC scheme. And so here we assume 256 bits. The ECC schemes that we simulate and run experiments with, in the real devices, the ECC scheme is unknown, right? Because we cannot observe it and it's not provided by the manufacturers. In simulation, we assume a wide variety of different ECC schemes that are possible, including Hamming single error correcting codes, stronger BCH codes capable of double and triple error correction, and even repetition codes, which are very simple and provide odd values of redundancy. The data patterns that we assume are in experiment, we use random data patterns, and in simulation, we use both random and data pattern of all ones. And we will show later that this is, it's very interesting to see the difference between the data patterns compared to what happens in experiment. And finally, the error mechanism that we study in both cases is data retention, though in theory, this analysis could be applied with other error mechanisms. So finally, I'll talk about our map estimation methodology before we jump into the results. So for our map estimation, we assume a uniform prior distribution, and we do this because we want to avoid biasing our results towards any particular preconceptions. And it also serves to demonstrate ein in the worst possible case where we have no information about which which on-die ECC scheme is more likely. And so to perform the map estimation, we simulate 10 to the 6, 256-bit ECC words per ECC scheme, and we perform error estimation using bootstrapping with 10 to the 4 samples. So now I'll jump into our results, essentially the results of our map estimation. And so here I'm showing a plot, which I'll introduce step by step. So here on the y-axis, we show the negative log likelihood. And this is the log likelihood of the different ECC schemes. And note that here, a lower value means that the scheme is more likely. Along the x-axis, we're going to show different ECC schemes, which are parameterized by the values shown there. And for example, here, I show a BCH double error correcting scheme, right? And so this bar shows the log likelihood observed. And we see that the confidence interval here is extremely tight because we're dealing with many, many samples. Now here I show the 8 most likely ECC schemes that we observed throughout our analysis. And we see that they spread across a variety of different ECC schemes, right? We see single and double error correcting codes, BCH and Hamming codes. But the most important one is the most likely ECC scheme shown on the right. And all of the other ECC schemes found are less likely models to explain the data that we observed. And so our conclusion from this analysis is that ein effectively infers the ECC scheme in LPDDR4 devices with on-die ECC to be a 128 plus 8-bit Hamming code. And we find that this is actually consistent with prior publications about LPDDR4 devices and some articles from manufacturers and so forth. And so we believe that this analysis is a faithful analysis, essentially. And second, we also observe that ein infers this information without any visibility into the ECC mechanism, without disabling ECC, and without tampering with the hardware in any way. So one thing that we would like to note is that ein applies beyond just on-die ECC as we demonstrated here. And so ein technically applies for any device where there's a communication channel that's protected by ECC. We can induce uncorrectable errors. For example, here we use data retention errors, but if an analogous error mechanism exists to exploit, we can potentially use ein. And that these errors follow predictable statistical characteristics. So 2 examples of such devices are DRAM with rank level ECC. So if the ECC contained within the CPU is somehow inaccessible, or the user wants to infer it for whatever reason, ein can potentially be a good way to do this in a manner very similar to what we did with the LPDDR4 devices that we showed. And another example is flash memory ECC, where the ECC is typically packaged within the NAND controller and not accessible by the system and has secrecy concerns and so forth. Okay. So finally, I'd like to conclude with just mentioning that there are a lot of other contributions in the paper that I didn't describe in the talk here. And we show more formal derivations and more data and so forth. And if you're interested, then please go ahead and look at the paper. So I'll stop here for now and take any questions that we have related to ein.
Maybe I'll ask one question again, Minesh. I think I'll encourage other people to also ask questions. I mean, certainly this is very important work, in my opinion, given that this information is not provided by manufacturers. So I have two questions related to that. Maybe you will cover this toward the end of your talk. But first of all, given that manufacturers are not willing to disclose their on-die ECC, you said that we're relatively confident. We're quite confident that what we find is actually what's implemented. But is there some other way of verifying? Or were you able to verify with any of the vendors the results?
Yeah, that's an excellent question. I think the answer is that for the second part, at least, no, we were not able to officially confirm with the vendor in any official capacity, right? Because this information, even in our experience, even with non-disclosure agreements and so forth, manufacturers are unwilling to discuss the details of the on-die ECC mechanism. However, we do have some measure of confidence in these because there are, I guess, prototypes of these devices that are published and described about in conferences. For example, for LPDDR4 devices, a slew of papers in ISSCC between 2014 through 2017 propose LPDDR4 designs that use the exact ECC code that we identified. And similarly, some white papers from manufacturers have hinted towards that scheme being the case. And finally, later in our talk, we use other methodologies to uncover the exact same information. And so putting all of those together, we have some amount of confidence, but we would not guarantee that this is the correct result. Mm-hmm. Only the manufacturer can really provide that information.
Sure, and that makes sense, of course. Yeah. Related to this, maybe turning the question backwards. Clearly, there are good reasons why manufacturers are unwilling to provide this information, right? At least good reasons from their business perspective, so that they don't lose competitive advantage. But suppose at some point they decide to provide this information. Now my question is, does that make this work obsolete? Or are there contributions in this work that will live beyond this disclosure, let's say?
Yeah, no, that's an important point to make. So I think there are, personally, I believe there are several points to our work that are sort of, long-lived beyond just applying it to a particular given DRAM device. So the first part is that, so I'm going to move to a slide that I talked about just real quick where we said that it's, yeah, so this slide sort of gives my point, I think, that this methodology, while we do demonstrate it for DRAM with on-die ECC and with data retention errors and so forth, those are all examples to put this in a very concrete context and show that this works. However, it is in concept a much more general approach, right? Because for any error mechanism that is well understood and that we can compare, what we expect to happen, which in this case we do using simulation, with an experiment where it actually happens, we can apply this methodology. And I give two examples here of rank level ECC and flash memory ECC, but you can conceive of any memory device where there's an ECC scheme in the way. It need not be on die. It could be within the interface between the memory and the controller, or it could be packaged within the memory device. But in any form, it's inaccessible. And EIN would enable you to recover not only the details of the on-die ECC, but also details of the error mechanism itself. And I think it's important to note that those details of the error mechanism itself are not something that the manufacturer can simply disclose, right? Because it's a very complicated sort of analysis with different error rates and characteristics under different conditions. And it really needs a lot of information to be communicated to describe those well. And even if you full well know what the ECC scheme is, you can still use EIN to infer those error characteristics, because even if you know the ECC scheme, that doesn't mean you can bypass it. Yeah, I think that the second piece that I wanted to mention was the simulation infrastructure that we developed, because it sort of allows this sort of approach to be used in a very straightforward manner, right? So it's, I think, a first piece or sort of like an initial exploration of how to apply this type of methodology. But I can imagine there are many other use cases where, even if our simulator doesn't immediately apply to those scenarios, because let's say we're using a different error mechanism, we believe that it's very extensible and can form the basis of a similar approach or let's say an analogous approach for a different technology or different device.
Yeah, that makes sense. Thanks. And I agree. I think there's certainly a lot of value to this work, even if the manufacturers decide to disclose their ECC schemes at some point.
Right.
Thanks. I think there is one more question on YouTube, and I'll let Geraldo handle that.
Thanks, Honor. Yes, we have one more question on YouTube. So the question this time is, what happens if the ECC scheme is not is none of the ones of those over which the prior work is taken? Also, given the statistical flavor, the person was wondering if the machine learning approach could work well also here.
Yeah, I thank you very much for asking both of those questions. I think they are very relevant. So the first point that, yeah, potentially these schemes that you consider or choose to evaluate the analysis over, they might not actually include the real scheme. And that's a very real concern. I think in our paper, we addressed this as a potential limitation of the work because it's true that if, for example, in the analysis we demonstrated, if we had not chosen the scheme, then our conclusions could potentially have been incorrect, right? We might have observed the second most likely scheme and believed that this is the result. So I think there's 2 points that I would like to make for this. The first is that this analysis, basically carrying off of what Oner said earlier, this analysis does give us the most likely scheme based on what we considered, but it does not give us the answer. I think we don't ever want to claim that this is the result and that it is correct, right? It's an analysis that tries to infer and reverse engineer some information based on what we can observe and what we know. And we really have no good way to verify this result. The second point I want to make is that we believe that it is unlikely that we would miss out on the correct scheme because, for example, for on-die ECC, these are very latency sensitive, area sensitive, energy sensitive mechanisms that are built exactly, built into the memory chip itself. And so there's a relatively small number of feasible mechanisms to use. In fact, one could even argue that using a double error correcting code inside on-die ECC, especially for a first generation implementation of on-die ECC, is potentially infeasible, or if it's not infeasible, it would be very expensive and maybe questionable. And so I think we can pretty reasonably enumerate a set of possible ECC schemes to use, both through just speculating which schemes are most likely, also looking at prior works and white papers and things like this. I think to answer the second question about potential machine learning approaches, I think that is absolutely a possibility here. So what we perform here is a statistical inference that's very sort of well-defined, and we controlled all the aspects of it. But potentially using an inference technique that's more general and potentially less supervised by our initial assumptions or something like that, can potentially do two things, right? So first, maybe it won't be so limited to the schemes that we initially define, because we can define the search space in a more general way. So as opposed to saying specific ECC schemes, perhaps we can figure out more details of the actual algorithm and then express that in a way that's not specific to schemes that we pick, but rather just error correction coding in general. But I mean, that's clearly speculation, and we haven't explored that problem ourselves. But second, it can do this in a way that, in a much more general sense for more devices, for more codes. And I do believe it's a promising direction for future work. Yeah, I think that concludes my answer. If that didn't answer your question, please go ahead and follow up.
Thanks, Minesh. There is no further question on YouTube at the moment. So
perfect. Okay. Okay, I think then I would like to take a short break at this point, because we have, we've talked about a lot of work, and maybe you want to go look at the component works, or just take a break from the presentation. And I think maybe we can reconvene in 5 minutes or so. I don't know. What do you think is appropriate, Geraldo?
I think 5 minutes sounds reasonable. I think it is okay.
Okay. Okay.
Because after that, I guess we have at least 3 more works to cover, right? So it would be good to
yeah. So we have these two papers
and the conclusion
and the conclusions. Yes.
Yes.
So okay. So yeah, let's break for 5 minutes, and then we'll reconvene and continue on with the material.
Okay, and feel free to ask your questions on the YouTube chat during the break. We're going to address them as quick as possible.
Thanks, Charles.
Thank you. Hello, that was 5 minutes. I guess we can get started again.
All right, perfect. Thanks, Geraldo.
Nice.
Okay, so I'll move into the next contribution, which is beer, where we deal with the on-die-ECC logic in much more detail. So as usual, I'll start out with a high-level summary of this work. So the problem that we tackle here is that DRAM on-die-ECC complicates third-party reliability studies, and this is very similar to the motivation for our previous work, iron, right? So here, the proprietary design of on-die-ECC obfuscates raw bit errors in an unpredictable way, and this interferes with design, test and validation, and characterization studies. And so our goal is to understand exactly how on-die-ECC is obfuscating errors, right? And so to this end, we make two contributions. First, we introduce beer, which is a new testing methodology that determines a DRAM chip's unique on-die-ECC function. In other words, its parity check matrix. And beer exploits ECC function-specific uncorrectable error patterns to do so, and in this way, it requires no hardware support, inside knowledge, or access to ECC metadata. Our second contribution is BEEP, which is a new error profiling methodology that we introduce, which infers the raw bit error locations of error-prone cells from observed uncorrectable error patterns. Now, in our evaluations, we apply beer to 80 real LPDDR4 DRAM chips from 3 major DRAM manufacturers, and then we show beer's correctness in simulation for a variety of representative simulated ECC codes. We hope that both beer and BEEP enable many valuable studies going forward. So I'll start off by talking about the challenges caused by unknown on-die ECCs. And so we saw this a little bit earlier. I'll just quickly recap. So there are a variety of third-party DRAM users, including system architects, test engineers, and research scientists, all of whom need to understand a DRAM chip's reliability characteristics. And this includes many different aspects, right? Like variation between chips, weak cell locations, and so forth. And so now we have on-die ECC, and a typical on-die ECC design is a 128-bit single error correcting code, a single error correcting Hamming code, similar to what we talked about before. And here we're illustrating a DRAM chip that uses on-die ECC. So we see that there's an ECC encoder and decoder fully contained within the chip. And this also means that it's invisible outside the DRAM chip, right? And so there are many ways to actually implement this 128-bit Hamming code. These essentially correspond to different ECC functions. And these are known as parity check matrices or H matrices. And all of these matrices correct a single bit error, but they act differently on 2 or more errors, essentially on uncorrectable error patterns. And manufacturers are free to choose any design that they want, according to maybe circuit optimization goals, such as area or power, and the details of which exact choice they make are highly proprietary, even under non-disclosure agreements. And so in the context of error characterization, this makes things very complicated. So let's take a look at the effect of different on-die ECC designs. So in this, I'm going to show some example data. And here we simulate uniform random errors within a 32-bit ECC word. And so the x-axis here shows the bit index in this 32-bit word, and the y-axis shows the relative probability of observing an error in each of the different bit positions. Because we're simulating uniform random errors, the per bit error probabilities are roughly equal pre-correction. And so what we see here is that it's essentially a uniform distribution. Excuse me. So now we see that the post-correction errors actually look quite different. So here we show 3 different 32-bit Hamming codes that are all single error correcting codes, and they each use a different parity check matrix. And what we see is that the post-correction errors are highly non-uniform and actually depend on the particular ECC function used. Our takeaway from this analysis is that essentially, excuse me, I lost my position here. Our takeaway from this analysis is that the same error characteristics can appear very different with different ECC functions. Now, let's take a look at some of the challenges this introduces for third-party studies. So for system architects who are designing error mitigation mechanisms, this makes these error characteristics unpredictable and chip dependent. And so the system designer can no longer understand exactly how the errors occur and mitigate them effectively. For test and validation engineers, on-die ECC introduces challenges for post-manufacturing testing. And this is especially because it hides the root causes of uncorrectable errors, and it defeats test patterns that are designed to target physical cells in specific ways. And finally, for research scientists, on-die ECC conflates the raw bit errors that are observed with artifacts from on-die ECC, effectively obfuscating the true physical cell characteristics that we want to see. And we note that all three of these challenges arise from the inability to predict how ECC transforms error patterns. And so to overcome this, our goal in this work is to determine the on-die ECC function without using any hardware support or tools, prior knowledge about on-die ECC, or access to ECC metadata. For example, access to the ECC syndromes or parity check bits. And so here I show the example from before with the F encode and F decode representing the ECC encoder and decoder. And what this goal means is that we want to know exactly what's happening within the encoder and decoder, because this would reveal exactly how on-die ECC scrambles errors and allows us to infer raw bit error locations, which we'll see through beer and beep later in the talk. So now I'm going to introduce beer and talk about what it is and how it works. So here I reproduce the typical on-die ECC function that I showed earlier. So let's talk about some important characteristics here. So both the encoder and decoder use linear operations. And so we can think of the encoder as a black box that accepts a data word and outputs a code word. Within this black box, the data word is multiplied by a generator matrix to form the code word. And this defines the linear transformation that happens. Similarly, the decoder accepts a code word prime, which might contain raw bit errors, and outputs a data word prime, which may contain uncorrected errors. Now, within the decoder, the code word prime is multiplied by a parity check matrix H. Together, G and H define the ECC function that we're trying to determine because they describe exactly how the on-die ECC is obfuscating errors. So this is exactly what we want to know. Now let's take a closer look at the ECC decoder. So decoding is typically done using a two-step algorithm that's called syndrome decoding. And so we first calculate an error syndrome that points to the error locations, if any, and then we correct any detected errors that were found. And so this illustrates the process of multiplying the code word prime with the parity check matrix H to create the error syndrome. And here we show a single bit error that occurred in code word prime using the red dot. After computing the error syndrome points us to the bit exact location of the error, if any occurred. And so this is how it works essentially for correctable errors. For uncorrectable errors, however, the situation is different. And so here we show a multi-bit uncorrectable error pattern in 3 different bit positions within the code word prime. Now, assuming we're using a single error correcting hem encode, the syndrome will point to an arbitrary position that depends on the particular H matrix used. And then the on-die ECC logic will simply flip the bit at that position, potentially exacerbating the number of errors, or maybe even correcting one of the errors that has already existed. And so our key idea here is to exploit this H dependence of uncorrectable errors in order to disambiguate different on-die ECC functions. And so let's take a look at how we determine the on-die ECC function using uncorrectable error patterns. And so our approach to doing this is to iteratively isolate the linear components of the H matrix. And a similar approach was demonstrated by prior work for rank level ECC, which has its own challenges. And so here we're developing a different approach that's useful for on-die ECC. And so I'll illustrate the high level concept of this approach. And so let's say we start with an error-free code word C, and we inject a single error in bit position 0. And so we illustrate that as a 1 in the code word prime. Now, when we compute the error syndrome, the single error isolates the first column of the parity check matrix because that's how the matrix multiplication works out here. And this means that the generated error syndrome is exactly equal to the first column of the H matrix. And through this approach, we can systematically extract every single column of the H matrix by individually extracting each of the columns. And through this process, we can determine the entire H matrix. Unfortunately, there are 2 major challenges to applying this approach to on-die ECC. First, there's no way for us to really inject errors in a particular bit because it's all contained within the DRAM die. The second is that we have no way to observe the error syndrome that's produced because on-die ECC does not provide feedback on correction events. So let's take a look at how we deal with these. The first challenge that we need to overcome is injecting errors in specific positions, and we achieve this by deliberately inducing data retention errors. And so we saw data retention errors before, and they're relatively easy to induce by simply pausing DRAM refresh operations. And once refresh operations no longer occur, data retention errors can occur, right? So one important property that we note is that a cell that starts out initially charged, shown as the blue curve in the figure on the right, will eventually fail basically down to 0, down to the cell voltage of 0 once the data retention error occurs. However, a cell that starts out initially discharged will actually stay discharged. And this is a data dependence property of data retention errors. So we can exploit this difference between the charged and discharged cells to restrict data retention errors to specific bit positions. And so an example of how we might do this is shown here. So on the left, we show a test pattern that we might write to a device. And here we write a test pattern of say 1000. And let's say that only the 1 is in the charged state. Now, after ECC encoding, we assume that the data is stored using, the data bits themselves are stored unmodified. And this is referred to as a systematic encoding, and is a very reasonable assumption for the on-die ECC code. The data might be encoded as such, and the errors are actually limited to specific bits within the device, because the bits that are stored in the discharge state, here shown as 0, cannot experience data retention errors. And so effectively, we've injected errors in any one of the highlighted bits, right? Because the errors are limited to those positions. So now let's take a look at the second challenge, which is inferring error syndromes. So let's suppose that we start with the same test pattern as the previous slide, but we now know that the ECC function sets precisely one parity check bit to the charge state for sake of example. And here, instead of 1s and 0s, I illustrate this with C and D corresponding to charged and discharged. So when we induce errors now, there are several different pre-correction error patterns that might occur. And we can think of this as all the different combinations of these charged bits, say. So the first case is where we have no errors and neither of the charged cells flips. The second case is a correctable error where only one of the charged cells flips to the discharge state. And the third case is the case of uncorrectable errors, where both charged cells flip to the discharge state. Now, in each of these cases, depending on the ECC function, the ECC decoder can create one of 4 possible data patterns here. And these are shown as HA through HD. And essentially, different H matrices will generate different error syndromes, which lead to different possibilities. And this essentially means that different H matrices will result in different uncorrectable error patterns in the case of uncorrectable errors. And so this allows us to differentiate different error syndromes from uncorrectable error patterns. So now the question is, which test patterns do we choose? And so in our work, we choose the set of n charge test patterns, each of which sets n bits to the charge state. And so here I illustrate what the 1, 2, and 3 charge patterns might look like, where with all the patterns that set 1, 2, or 3 bits to the charge state. And so our paper explains that the combined 1 and 2 charge patterns are sufficient to identify the ECC function. To test each of the patterns, we use to test each of the patterns that we use, we find all of the potential uncorrectable error patterns that can occur with that pattern. And so this occurs across multiple rounds of testing to identify all possible patterns. And we can do this very easily because data retention errors occur uniform randomly. And this means that even a single DRAM chip provides millions of samples of these errors. For example, a 2 GB DRAM module yields 2 to the 24 128-bit words. And across all of those 2 to the 24 words, it is extremely likely that we've observed all the possible combinations. So putting this together, we arrive at a 3-step methodology, which is BEER. So the first step is to experimentally induce data retention errors using the 1 and 2 charge test patterns. The second step is that for each test pattern, we identify all possible uncorrectable errors that can occur. And third, we solve for the particular ECC function that exhibits the observed behavior through the use of a SAT solver. So now I'll talk about evaluating BEER both in experiment and simulation. So I'll quickly cover our experimental methodology. So we test 80 LPDDR4 DRAM chips from 3 major DRAM manufacturers, and all of these DRAM chips use on-die ECC. And we anonymize the manufacturers as A, B, and C for confidentiality reasons. We're using a similar setup as the previous studies where we're using temperature-controlled testing infrastructure and we have control over the DRAM timings. We test with refresh windows ranging from 1 to 30 minutes at 30 to 80 degrees centigrade. And this leads to bit error rates, observed bit error rates between 10 to the -7 and 10 to the -3. And note that these bit error rates are far larger than the error rates of other error mechanisms that might interfere with our tests, for example, unwanted soft errors. And so by and large, we observe data retention errors all throughout the device. So let's talk about applying BEER to LPDDR4 DRAM chips. So in this experiment, we study the uncorrectable errors in the 1 charge patterns. And so we show the uncorrectable errors for a representative chip from each of the manufacturers labeled A, B, and C. The x-axis here shows the bit index into a 128-bit data word, and the y-axis shows each of the 128 1-charge test patterns, which are indexed by the position of the charged bit. So here we see that purple corresponds to rarely observed errors, and the yellow conserves to very frequently observed errors. And so what we're seeing here is for every test pattern on the y-axis, essentially how many errors occur in each of the different bit positions aggregated across all of the different ECC words in the device. So the first thing we notice is that the data retention errors occur across the y equals x line, and these are shown in yellow. And these correspond to data retention errors within the charged bits. So note that this is the one charged pattern. And so that single bit that's charged exhibits a data retention error, and that's what we're observing. Now, any errors off of the y equals x line are miscorrections, which are purely an artifact of ECC correction because they correspond to discharged data bit positions. And so all of these errors must have occurred when ONDI-ECC performs an undefined operation when faced with uncorrectable errors. Now, comparing these three plots, we actually see a very high variation between the three different manufacturers. And this indicates that the three manufacturers use very different ONDI-ECC functions. Finally, we see repeating structures within the miscorrections of manufacturers B and C, which indicates some underlying structure in the way their H matrix is organized. Now, we have two main conclusions from this study. First, we conclude that DRAM manufacturers appear to use different ONDI-ECC functions. And the second conclusion is that chips of the same model number appear to use identical ECC functions, which we show in our paper. So let's take a look at how we can use these miscorrections to solve for the ECC function. So to identify the exact H matrix that each chip uses, we use the Z3 SAT solver. Now, although we demonstrate and evaluate Beer for single error correcting Hamming codes, it readily applies to all the linear block codes that use a similar decoding process. And so we open source our Beer implementation on GitHub, and it can be found at the following link shown on the slide. Now, one thing that I would like to mention is that we face two limitations to validation of our results in the experimental studies. First, we have no way to check the final results since we cannot see into the ONDI-ECC implementation. And therefore, even though we obtain a result, we have no way to check whether that result is truly correct. And second, we're actually not allowed to share our final matrices due to confidentiality reasons with the manufacturers. And to overcome these limitations, we validate Beer in simulation, where we can evaluate Beer's correctness, overcome the confidentiality issues, and test a much larger set of ECC codes than possible with the limited set of devices that we test. So I'll quickly describe our simulation methodology. We use the EINSIM DRAM error correction simulator, which I described as part of the previous work, EIN. Here we simulate a large number of representative single error correcting Hamming codes with a wide range of data word lengths. And we also simulate 4 different data pattern combinations, the 1, 2, and 3 charge patterns, and the combination of 1 and 2 charge patterns. For each test pattern, we simulate 1 billion ECC words, which amounts to approximately 14.9 gigabytes for 128-bit words, which is more than a typical, say 8 gigabit device. We simulate data retention errors with bit error rates between 10 to the minus 5 and 10 to the minus 2 for purposes of our simulations. Now let's take a look at our correctness evaluation. So here we evaluate the number of unique SAT solutions that Beer finds, and this shows whether the unique ground truth solution is identified. So here, this figure's x-axis shows the ECC code data word length, and the y-axis shows the number of unique ECC functions that the SAT solver identified. Each data point here shows the minimum, median, and maximum values observed across all simulated ECC codes. So the first thing that we notice is that the 1 and 2 charge test patterns combined always find a single unique solution for all test cases. We also see that the 1, 2, and 3 charge patterns individually sometimes find more than one ECC function that can explain the observed uncorrectable errors. So we conclude that Beer successfully identifies the ECC function using the 1 and 2 charged combined test patterns. Our paper provides 2 other evaluations for Beer. First, we evaluate the practicality of Beer's SAT problem in terms of runtime and memory consumption, and we find that both are negligible for short codes and realistic for longer codes. Second, we evaluate the experimental runtime, and we find that the experimental runtime is largely bounded by waiting for data retention errors to occur. And in our experiments, approximately 4.2 hours of testing is used per chip. So finally, I will talk about BEAT, the error profiling methodology that we propose, and discuss some other practical use cases for Beer. So in our paper, we provide 5 use cases to show how knowing the ECC function can be useful in practice. The first use case deals with error profiling. We introduce BEAP, which is a new testing methodology that shows how knowing the ECC function enables identifying the bit exact locations of raw bit errors based on observing post-correction error patterns. The second use case deals with system design, where knowing the ECC function allows better architecting DRAM controller error mitigation mechanisms because they can now be informed about on that ECC. The third and fourth use cases deal with testing, where we can better craft worst case test patterns, knowing exactly how on ECC will encode the data and doing root cause analyses for uncorrectable errors. And the final use case deals with error characterization, where we can study the statistical properties of raw bit errors, for example, their spatial distributions, in a more detailed way than possible with just the high-level characteristics returned by a methodology such as EIN. So in this talk, I'm going to focus on this first use case dealing with error profiling and talk about BEEP in a little more detail. So the key idea behind BEEP is that knowing the ECC function, essentially via BEER, enables calculating raw bit error positions. So given a particular raw bit error, pattern, here we show 4 errors within a 7-bit word. The ECC decoder produces some sort of observed errors, and this corresponds to an uncorrectable error pattern. And if the ECC decoder is known, we can calculate what the raw bit error pattern is. And we explain exactly how we do this in the paper. So BEEP allows us to infer which physical cells are susceptible to data retention errors using only the observed errors after ECC decoding. So I'll quickly go through the high-level algorithm that BEEP uses. And so it goes through each bit step by step within the ECC word and keeps track of the error-prone cells it has identified as it iteratively tests. So the algorithm looks as follows. For each bit within the ECC word, BEEP first crafts a test pattern that targets the bit that it's targeted, it's currently testing. BEEP tests for data retention errors. And third, BEEP calculates raw bit error locations that correspond to the uncorrectable errors that it observed. And it goes ahead and repeats this for each bit within the ECC word. And so we evaluate BEEP's accuracy by measuring its success rate of identifying raw bit errors in simulation. And so we simulate varying ECC word lengths and bit error rates. And for each simulated measurement, we look at 100 different ECC words. And so in this plot, on the x-axis, we're showing the number of errors that we injected per code word. And so, for example, we inject 2, 3, 4, 5, and so forth errors per code word. And on the y-axis, we show this measure of success rate. And the different bars here represent different ECC code word lengths shown in colors. And the shades represent the probability that each of the injected errors fail. And we see from this analysis that BEEP is more successful for longer ECC words shown on the right-hand side of the plot because it has more errors to work with when doing its iterative process. And it's also more successful for higher probability errors. This is because these errors are simply more easy to observe. And so these are the 2 takeaways that we make from this analysis. And so the other information that's contained in the paper is dealing with the formalism for BEER and charge patterns, our evaluations in both experiment and simulation, and detailed discussions of our use cases, and finally a discussion on BEER's requirements and limitations. And so this concludes my talk about BEER, and I think I'll pause for questions at this point. I'm putting up the summary slide to jog the memory.
Minesh, maybe I'll ask one question again. Start the questions.
Sure.
So I mean, this is also a very important work, of course, and I should mention maybe this is related to some multiple of these works, but this BEER in particular takes advantage of data retention errors, right?
Correct.
Assume that you don't have data retention errors. Can a similar methodology be applied by exploiting some other types of errors?
Yeah, that's an important point. So we haven't attempted to do so, but we believe it should be possible for both this and some of the other works like EIN, for example. And this is because, so I'll use these two as an example, right? So EIN and BEER, at some level, both rely on the statistics of the errors, right? So we're not looking at a single ECC word here. We're looking at the distribution of errors across all the ECC words in the device. So I'm going to quickly move to this slide, which showed the miscorrections. So here we're aggregating the miscorrections that are observed across all the different words. And so we have not only the positions where the errors occur, but also the frequency with which those errors occur, right? So from a statistical perspective, this is very nice because, yeah, with data retention errors, this property is very concrete where, charged cells will fail, discharged cells will not fail. It's very binary. But if we consider another error mechanism that is also data dependent, but maybe not quite to this extent, right? Like maybe with some probability it fails if it's programmed to a particular pattern, and with a different pattern it fails with some other probability. So essentially the property we're exploiting here is this asymmetry that comes with data dependence. And so if such a mechanism, if such an error mechanism exists, we could theoretically apply it in the same way here. It's just this data would be far more, let's say, noisy even, because we would be trying to distinguish different probabilities as opposed to a yes or no event. But it should very much be possible with enough data samples and enough fidelity. Potentially here, you might need to test many more devices and collect a lot more data. But we do believe that should work. And prior studies that have looked at other error mechanisms, like, for example, errors that occur when you reduce access timings, or even Rowhammer, have shown that there is some amount of data dependence involved. It might not be as clear cut as with data retention errors, but it is there. And the fact that it's there means that it is potentially exploitable at some statistical level.
That makes sense, I think. So that could be good. That could be a good avenue for future work if you don't have retention errors. Clearly in DRAM, retention errors are difficult to avoid, but in perhaps some other memory technologies, they will not lead to this sort of nice and abundant data, or you may need to wait for a really long time to get the retention errors right.
That's right. And in that case, yeah, a different error mechanism would be preferable. And I think, sorry, something just to add real quick. I think, yeah, potentially that limitation sort of exists here too, right? Like, so as I was explaining, the data retention error experiments that we conduct, you do spend a lot of the time in the test simply waiting for data retention errors to occur. And from the perspective of quickly testing many devices, that can be a limitation. But if potentially somebody did extend this analysis to another error mechanism, potentially in the way that we discussed or in some other way, if that error mechanism can be tested for very quickly, then yeah, it's potentially an enhancement over this methodology even. So I think there are directions for future work here. Absolutely.
Yeah, certainly. I agree. I mean, latency, as you mentioned, the errors that result from reducing latency could be a possibility, or voltage could be a possibility, but the data pattern dependence is not as clear cut in those. Rowhammer is probably the most, let's say, potentially a second best mechanism that comes to my mind, because there's certainly clear data dependence in Rowhammer. But again, it may not be as nice as data retention.
Right. It's yeah, another aspect there is, I think, also achieving the ability to observe a lot of uncorrectable errors. Potentially, data retention, the error mechanism allows you to induce errors everywhere at very high rates by just waiting more. With Rowhammer, it maybe is not quite so easy to achieve such high error rates. Or if you do, you might need to disable refresh operations, which then you're circling back to data retention errors in the first place. There's definitely an analysis to be done.
Yeah, certainly. Okay, I don't have any other questions at the moment. Maybe some others do.
We also don't have any questions from now on YouTube, so if there is no further question, maybe we can move to the next one.
Okay. Yeah, I'm happy to go back if a question shows up, or
yeah, that's great.
Yeah, so not to worry. All right, so I'll move on to our next core contribution, HARP, which tries to understand how errors appear outside of the DRAM device based on the effects of on-die ECC. So I'll, as usual, start with a brief summary of this work. So our motivation for this work is that state-of-the-art memory error mitigation mechanisms that deal with high error rates and technology scaling issues and so forth often require the processor to identify which bits are at risk of error. And we refer to this process as error profiling. Now, the problem is that on-die ECC complicates profiling because it alters how errors appear outside of the DRAM chip. And our goal in this work is to understand and address the challenges that ONDI ECC introduces for error profiling. And so to this end, we have two contributions. First, we analytically study ONDI ECC's effects and identify three key challenges that the error profiler needs to address. First, ONDI ECC exponentially increases the number of at-risk bits that need to be identified. Second, ONDI ECC makes individual at-risk bits much harder to identify. And third, ONDI ECC interferes with commonly used memory data patterns that are used to speed up testing. Second, we introduce hybrid active-reactive profiling, or HARP, which separately identifies raw bit errors and errors introduced by ONDI ECC. And in doing so, HARP effectively reduces profiling with ONDI ECC into a problem of profiling without ONDI ECC. Through our evaluations, we demonstrate that HARP overcomes the three challenges that we described. We show that HARP identifies all errors faster than two baseline profiling mechanisms, which sometimes fail to achieve full coverage of at-risk bits. And we provide a case study that shows that HARP identifies all errors faster than the best performing baseline, as an example result by almost 4x given a raw bit error probability of 0.75, which I'll describe further in our evaluation section. Okay, so I'll start off with a quick overview of memory error mitigation and profiling. So let's take a look at scaling related memory errors. So as manufacturers scale storage densities, various technology-specific errors occur. Here are three examples of scaling-related errors from DRAM, which occur for various circuit-level reasons. So we talked about data retention. There are also challenges with write recovery and variable retention time. And these are all essentially exacerbated by continuing to improve density. Now, the key point that I want to make here is that each of these error mechanisms manifests as uncorrelated single-bit errors. And these represent the primary scaling challenge for continued DRAM technology scaling today. Now, as error rates continue to increase, we typically need more and more sophisticated error mitigation solutions. So here's an illustration of the types of error mitigation mechanisms that are suitable at different error rates. So in the past, error rates have been low enough such that no mitigation was really necessary for simple or potentially simple mechanisms such as row and column sparing. Today, manufacturers are using ONDI ECC to mitigate moderate error rates. In the near future, prior works project that advanced solutions will be necessary to manage high error rates up to and exceeding values of 10 to the minus 4. So let's take a look at some examples of these advanced solutions. Now, error mitigation is a huge research space with solutions that span the entire system stack. And so here are some examples of error mitigation techniques in the software. These include things like page replication, page retirement, task replication, and fault tolerance techniques within the processor, including bit repair techniques, error correcting coding, and checkpoint recovery mechanisms, and within the memory itself, such as row and column sparing and ONDI ECC. So the cost and efficiency of each of these mechanisms depends on the particular error characteristics that need mitigation. And at the high error rates that we expect in the future due to technology scaling, state-of-the-art solutions follow the bit repair approach. And these are what we primarily focus on in our work. So let's take a closer look at repair mechanisms. So these techniques first identify and then repair any bits that are at risk of error. And so here we have a picture of a system that uses a repair mechanism. On the right, we have an unreliable memory that contains an error-prone data store. And on the left, a memory controller that contains the repair mechanism. The repair mechanism itself repairs any bits that are marked as at risk within an error profile, which you can essentially think of as a list of at-risk bits. Now, when the CPU performs a write operation, the data is written through the repair mechanism into the unreliable memory. When the CPU performs a read operation, the data is first repaired before being returned. And when essentially the repair mechanism can only repair bits that are known to be at risk, essentially which are contained within the error profile. And so as a consequence, the repair mechanism is dependent on identifying at-risk bits. And we refer to this process as error profiling. So let's take a look at how error profiling is typically done. So here I am going to show a quick flowchart of a typical error profiler. So there are typically two major types of profilers, which we refer to as active and reactive profilers. Active profilers deliberately induce worst-case conditions to exacerbate errors. And in contrast, reactive profilers passively monitor the memory device to discover errors as they occur. So regardless of the approach, both approaches check for errors that occur and then mark these erroneous bits as bits at risk of error. And this process repeats until all the at-risk bits are identified. Now, a key point to note here is that this process depends on observing an at-risk bit fail so that it can be marked as at risk in the error profile. And as we've talked about before, on.ECC interferes with these observations. So let's take a look at how on.ECC affects this. So on.ECC changes how errors appear to the profiling mechanism. And so here's a diagram showing how on.ECC interferes. As the profiler reads and writes data, on.ECC has some effect on the errors. And we actually want to know what that effect is and understand what it causes. And so our goal in this work is to understand and address any challenges that on.ECC introduces by changing how these errors appear. So this leads me into our study. So let's talk about how on.ECC impacts error profiling. So the profiler's goal in general is to identify all of the bits that are at risk of error. And so here is the profiler's view of memory errors in a memory chip with and without on.ECC, shown left and right, respectively. In both cases, the profiler cannot actually see into the memory device, and so it doesn't know what's happening in the physical cells. Instead, the profiler simply observes errors at the chip interface and declares those bits to be at risk of error, regardless of what's actually happening within the memory itself. So let's take a closer look at what happens without on.ECC. So without on.ECC, there's only one source of errors, and this is when the physical underlying bit fails. And so here's a diagram which illustrates this. So when the bit inside the memory chip fails, an error is observed at the interface. And we refer to this as a direct error because the observed error is caused directly by the underlying bit failing and for no other reason. In this case, the profiler observes two errors and identifies both of these to be at risk. Therefore, the error profile is calculated simply as the union of all observed direct errors. However, with on.ECC, there are now two different sources of errors. Here we illustrate the on.ECC process inside the memory chip. And note that, again, we're assuming a systematic encoding, which means that the data and metadata are stored separately. Now, at the interface, the profiler observes two errors, let's say. However, we categorize these errors differently. The first error shown in the left is a direct error because it corresponds to an error within the data bit within the memory device. And due to the systematic encoding, an error at that first bit position corresponds to an error after on.ECC decoding. The second type of error is what we refer to as an indirect error, and this occurs exclusively as a result of on.ECC. And essentially, this is what happens when on.ECC performs a miscorrection to mistakenly correct a bit that it thinks is at risk of error. And the error profile in this case is essentially calculated as the union of all direct errors and indirect errors. Now let's take a closer look at indirect errors because they have severe implications for profiling. The key point is that indirect errors depend on the raw bit error pattern that occurs. So here we have the same example as the previous slide, where there are 3 bits at risk of error, where X represents at risk. So let's take a look at 2 example raw bit error patterns that can occur as a result of these bits at risk of error. So we refer to these as pre-correction error patterns, in contrast to post-correction error patterns that would occur after on.ECC correction. So in these examples, we see that both pre-correction error patterns have the same direct error observed at the leftmost bit. And so this error is observed directly after on.ECC correction in both examples. And so, yeah, we see that it's at the same position as the underlying errors. Unfortunately, we see that there are 2 indirect errors that occur, and these occur in different bit positions. And this is because the raw bit errors look differently in each case, and the on.ECC performs a different operation. And so the key observation from this study is that on.ECC introduces statistical dependence between bits that are otherwise independent. And as a result of this, on.ECC introduces several challenges for error profiling. So let's talk about 3 challenges that we identify in this work. First, on.ECC exponentially increases the number of at-risk bits that the profiler needs to identify. Second, on.ECC makes each individual at-risk bit harder to identify because each bit at risk of post-correction errors can only be exposed given a specific raw bit error pattern. And third, on.ECC interferes with commonly used memory data patterns because now the profiler must consider combinations of raw bits instead of just individual bits alone that the patterns are designed for. So let's talk about each of these challenges one by one in a little more detail. So the first challenge is essentially a combinatorial explosion of errors. So let's take a look at the same example that we had from before. We have 3 pre-correction errors that we label as 0, 1, and 2. Now here are all the different possible combinations of the pre-correction errors that can occur. So we have the empty set, we have each of the bits 0, 1, and 2 occurring individually in pairs, and then all 3 of them at once. Now, the 4 sets on the left are correctable, and so there won't be any post-correction errors corresponding to there. However, the 4 on the right correspond to uncorrectable error patterns, and so these 4 can actually result in post-correction errors. Now, in the very worst case, each one of these individual combinations can potentially introduce a unique indirect error. So let's take a look at what this means for the profiler. So here we have the same example from before, where there are 3 pre-correction at-risk bits within the memory chip. Now, after on-die-ECC correction, what this can cause is that the leftmost bit will be at risk of direct errors because the underlying corresponding bit is at risk of pre-correction errors. And all of the other post-correction bits can potentially experience an indirect error as a result of various combinations of the at-risk bits before on-die-ECC correction. And what this means is that we have an exponential increase in the number of at-risk bits that the profiler needs to identify. So this table summarizes this combinatorial explosion. So given n at-risk bits pre-correction, we end up with 2 to the n minus 1 at-risk bits post-correction in the very worst case, where every combination of pre-correction errors introduces a unique indirect error. And so, as we see, we start with 2, 3, and 4 pre-correction errors. This quickly blows up to 3, 7, and 15 potential at-risk bits post-correction. And given, a larger number of pre-correction errors, such as 8, there's an absolutely humongous number of post-correction errors that we might have to deal with. And in this case, that's essentially a lot of work for the error profiling mechanism. So let's take a look at the second challenge, which we refer to as bootstrapping for reasons that will soon be clear. So on-die-ECC makes identifying each bit at risk of indirect errors difficult. This is because observing the bit fail requires a specific pre-correction error pattern to occur. However, the profiler cannot actually see pre-correction errors, so it doesn't know which pre-correction error pattern has occurred. And so this results in a vicious cycle where the profiler must test a bit, but it cannot know whether the bit has actually been tested, all because it does not know what's actually happening with the pre-correction errors. And so as a result, the profiler must exhaustively test all possible cases one at a time in order to identify at-risk bits, which, as you can imagine, is a very slow and laborious process. And we'll show in our evaluations that this results in very slow profiling. The third challenge relates to memory data patterns. So profilers typically use a common set of data patterns, such as illustrated here, where different physical cells are programmed to meaningful values. So these patterns deliberately induce worst-case circuit behavior in order to maximize the chance of identifying errors. And so the goal here is to accelerate the process of profiling and exercise different failure modes that can lead to errors and so forth. So on-die-ECC actually breaks these data patterns in 2 different ways. First, on-die-ECC encoding turns a carefully designed data pattern into something that's obfuscated and unclear. And so the original intent behind a data pattern is potentially defeated. Second, on-die-ECC takes conventional data patterns that induce single-bit worst-case conditions into something that requires multi-bit worst-case conditions because pre-correction error combinations are required to expose errors. And as we discussed in our paper, this is difficult to design and use in practice. So now let's talk about how we can use these observations to develop HARP, which is our proposed profiling mechanism. So our key observation is that indirect errors can only be introduced by on-die-ECC's error correction process. And as shown here, what this means is that any number of direct errors may occur, depending on which bits are at risk of pre-correction error, but only one indirect error may occur at a time, given a single error correcting code. And extending this to a more general argument, at most n indirect errors can occur concurrently, given an n error correcting on-die-ECC. And so we form a 2-part key idea based on this observation. First, if we can somehow identify all direct errors, we can safely rely on a secondary ECC to identify the remaining indirect errors. So here's an illustration showing how a secondary ECC within the memory controller can actually be used to conduct profiling. With sufficient correction capability, the secondary ECC can reactively profile for any indirect errors that are introduced by on-die-ECC and feed that information back to the error profile for subsequent repair. And we'll talk about this more in detail after, I guess, in a few slides. The second part of the key idea is that if we can read the raw data bits, but not necessarily the metadata bits, we can use existing profiling techniques to quickly identify all bits that are at risk of direct errors. And so here's an illustration showing how an active profiler within the memory controller can potentially use an ECC bypass path to directly read data from the data store. In this way, the profiler can profile for errors as if on-die ECC does not even exist. So HARP combines these two key ideas to create a two-phase profiling algorithm. First, HARP uses an active profiler within the memory controller along with an on-die ECC bypass path to quickly identify all bits that are at risk of direct errors. Second, HARP safely identifies all the remaining bits that are at risk of indirect errors using a secondary ECC in the memory controller. And this exploits the process that, exploits the observation that on-die ECC can only introduce at most n indirect errors given an n error correcting on-die ECC. Now, whenever either active or reactive profiling identify an at-risk bit, they report it to the repair mechanism for subsequent repair. So let's take a look at each of these components in a little more detail. So here is an illustration of how the ECC bypass path generally works. Here we have the data and metadata stored within the physical device, and we illustrate two different options for reading. On the left, we show a bypass path, which shows how the raw data is read out, and the ECC metadata is simply ignored. On the right is a normal read operation that goes through on-die ECC and potentially introduces indirect errors on top of the direct errors that already exist within the data bits. So this is an important distinction because it shows that the bypass path has low hardware cost. We're simply skipping the ECC decoding process and returning the bits internally, and is actually reducing the operations performed on the output path. Similar bypass paths have been proposed in prior works, and we discuss this further in our paper. Now, using this bypass path, the active profiler is able to use existing profiling algorithms as if there is no on-die ECC at all, and it can use this to very quickly and effectively identify bits that are at risk of direct errors. However, because the active profiler bypasses on-die ECC, it does not identify bits that are at risk of indirect errors, and this is a task that's left for the secondary ECC. So the key idea here is that active profiling reduces the task of profiling with on-die ECC into a task of profiling without on-die ECC with minimal modifications to the actual on-die ECC itself. So now let's talk about the reactive profiler design. The reactive profiler simply consists of secondary ECC in the memory controller with sufficient correction capability. For this, for implementing the secondary ECC, the system designer must choose a suitable secondary ECC mechanism that's appropriate for their particular system. Now, the ECC design space in general is huge, and HARP requires only one thing, that for an n error correcting on-die ECC, the secondary ECC must be able to correct n errors per on-die ECC word. And in our paper, we discussed the design details in a little more, detail, including the fact that this requires somehow aligning the on-die ECC and the secondary ECC words. But the details of how we do that are left to the system designer to match their particular system. As an additional optimization, we leverage the fact that knowing the on-die ECC implementation, in other words, its parity check matrix, allows us to predict indirect error locations. Note that this does not change the active profiling process. However, it provides a head start for reactive profiling. And so to illustrate this, we basically say that if we know that several bits are at risk of direct errors, we can predict which bits might be at risk of indirect errors using knowledge of the on-die ECC implementation. And so to achieve this, we introduced two HARP variants, HARP U, which is unaware of the on-die ECC implementation, and HARP A, which is aware. And in our evaluations, we show the differences between the two. So now I will talk about our evaluation methodology. So we evaluate HARP in a simulation because in simulation, we can accurately calculate error coverage. And this is a non-trivial task for chips with on-die ECC because there are many different possibilities, and accurately calculating coverage requires exploring all those possibilities. So in our simulation methodology, we inject pre-correction errors in each ECC word using 2 through 5 pre-correction errors per ECC word, and per bit pre-correction error probabilities between 0.25 and 1.0. And this represents a wide range of different pre-correction errors that might occur and how the profiler might deal with it. We also release our simulation tools on Zenodo and GitHub as open source tools. So in our evaluations, we compare with 2 different baselines. The first is naive, which represents typical prior round-based profilers that operate without knowledge of on-die ECC. And if you remember from our earlier talk about Reaper, this is very similar to the brute force profiling approach, and also the profiling algorithm that I presented earlier in these slides. The second comparison we make is against BEEP, which I talked about alongside BEER. And BEEP uses knowledge of the ONDA ECC implementation to craft data patterns that are specifically designed to systematically expose post-correction errors. Now, here I show an analysis of the coverage of bits at risk of direct errors, which is essentially the benefit of the active profiling phase. So bear with me, there's some complexity in this graph. So each of these 4 different windows shows the different per bit pre-correction error probabilities that we inject pre-correction errors with. And the x-axis for each of these plots shows the number of profiling rounds that elapse, and we evaluate between 1 and 128 profiling rounds for each of the different profilers. The profilers are shown in different colors. And finally, the different markers on each of the curves represent different numbers of pre-correction errors that we inject. And so in summary, all of these different curves represent different profiling configurations. And based on this analysis, we're looking at the y-axis, which is the coverage of direct errors that is achieved. And more error coverage is definitely better in this case. So we make several observations from this figure. So first, we observe that HARP achieves full coverage in all cases. And we see this as the HARP line quickly achieving a direct error coverage of 1.0, regardless of the different configurations that we use. This is in contrast to the baseline mechanisms. For example, BEEP fails to achieve coverage across all the different configurations. And we actually identify that this is because it does not effectively explore the different pre-correction error combinations that are necessary to expose all of the different direct errors. Naive, while it does appear to achieve full coverage across all the configurations, it does so slowly because similar to BEEP, it is incrementally testing different pre-correction error combinations, which is a slow and laborious process. The second observation that we make is that HARP is independent of the number of pre-correction errors that we inject, essentially shown by the markers for each of the lines. And this is very interesting because it directly shows that HARP is independently profiling each of the individual bits that are at risk of pre-correction errors without relying on different combinations of those errors. And so by independently identifying each of the bits, it doesn't matter how many bits there are, they're all profiled all at once. And so from this coverage analysis, we conclude that HARP overcomes all of the profiling challenges because it does not rely on combinations of pre-correction errors to achieve coverage. Now, there's a wealth of other information in the paper that I didn't include in this talk here, including a detailed analysis of ONDA ECC and this derivation of direct and indirect errors. We have a discussion about HARP's design decisions. We have many more evaluation results related to coverage of both direct and indirect errors, an analysis of a profile of bootstrapping, and a case study which examines the bit error rate before and after reactive profiling. And finally, we have a discussion about reproducing the artifacts to reproduce the results in our paper. So I think here I will pause for questions. So please go ahead.
Thanks, Minesh. I have 2 questions related to HARP, actually. My first question is related to the secondary ECC that you proposed to perform the reactive profiling. So people can say that this solution is potentially costly because we need a secondary ECC. Did you think about alternative solutions, potential software-driven ones, and to do the reactive profiling, so it would be cheaper? And what are the drawbacks of other alternative solutions?
Okay, yeah, that's a great question. Thanks. I'm gonna open up to one of the slides I presented earlier where we talk about the requirements necessary from the secondary ECC. So this slide describes the design of the reactive profiler, right? And while we do show secondary ECC here, it's not necessary that a secondary ECC be used for this process. Excuse me. The key point to make here is that given that ONDA ECC can introduce at most n indirect errors at once, whatever mechanism is used for reactive profiling simply need to be able to manage that many errors, right? And ECC is sort of a natural fit for this, given that a lot of commodity systems today already have secondary ECCs within the CPU or the memory controller and so forth. For example, rank level ECC. And also secondary ECC provides a very neat correction capability. So for every ONDA ECC word, secondary ECC could potentially provide that correction capability in a very obvious manner. However, as you said, other techniques can potentially be used to perform this reactive profiling. So if we consider even a software level approach, say some sort of mechanism that uses replication, right, like task replication, potentially whenever an error is discovered there, the software mechanism has a way to discover that an error has occurred and recover from the error, maybe by reverting to a previous checkpoint or exploiting some redundancy within the software itself. In this way, we can also profile for indirect errors, and this information could potentially be reported back to the repair mechanism, maybe by some interface for the software to update the error profile or what have you. So this mechanism is in no way is specific to secondary ECC. However, the actual trade-offs involved and the downsides here, they're rather difficult to analyze because there is such a large space of potential techniques that can be used for this. So I'm going to move back to the slide I presented at the beginning with the different possibilities here, right? So we do have error mitigation mechanisms at all levels of the stack, and this is just a small example of all the proposals that have been made. So deciding which is the best fit for a particular system it's very difficult to say, right? So we can go off of several different directions. So first, if we know that the error rates that we're tackling are relatively high, say, we expect many multi-bit errors across many different ECC words, perhaps a software granularity mechanism is not the best because it might need to operate at a very high at a very coarse granularity, where you might have many errors that occur all at once and overwhelm the mechanism. In contrast, a bit repair technique or something similar is designed to combat very high error rates. And so maybe something like that is more suitable. But in contrast, if the error rate to be expected is very low, maybe the overheads of a hardware-based mechanism are not desirable, or it's too inflexible and so forth. And then maybe a software solution is preferable. So I think it very much depends on the system designer's goals and the particular system and the errors that need to be targeted, and potentially lots of other factors too. So it's hard to give a single answer. Does that answer your question? Makes sense?
Yeah. Thanks so much. That is a great answer.
Okay. Perfect. Thanks.
And I have a second question that is a little bit off scope, but since HARP, the reactive profiling in HARP with the secondary ECC kind of reduce the errors in the ECC words to like 1 bit type of access, would it can we use that same mechanism to prevent row hammer attack at some degree, or have you thought about that, or there is a prior limitation to that?
Yeah, I can't. So we haven't thought about this in detail, but based on my initial thoughts, sorry, I want to move to a slide to exemplify. Sorry, one moment. I'm looking for the appropriate slide.
No problem.
So, right. So here's the slide that sort of described the purpose of a repair mechanism, right? So a mechanism like HARP or some other error profiling mechanism is essentially in support of the mechanism that actually repairs the errors, right? The error profiler itself is not doing the actual error mitigation. And so I wouldn't say that HARP, is sort of a way to prevent row hammer errors or anything like that. I think the answer to that depends very much on the particular repair mechanism that you use. So in the scheme that HARP describes, what happens is that the repair mechanism is first informed of which bits are at risk, and then it repairs those bits. And then any remaining errors that occur due to indirect errors that weren't initially identified will slowly be identified by the reactive profiling. But in either case, the repair mechanism is the one doing the actual mitigation. Now, for row hammer, I think there needs to be more analysis done to determine whether the error model for row hammer is well suited to a repair mechanism like this, because it is conceivable that maybe if there is an appropriate profiling algorithm that is developed for row hammer errors and quickly achieves high coverage, that algorithm can be used by HARP during the active profiling phase. In this way, most of the bits at risk of direct errors due to row hammer will be identified and put in the error profile, and the repair mechanism will be able to deal with them. However, this means that the active profiler needs to achieve high coverage of those bits. In order to achieve HARP's guarantee, it needs to achieve full coverage. And it is unclear whether row hammer errors are so easily discovered today, because I think we don't have that much information on it, and there's evidence of certain errors being repeatable, but also evidence of other errors not being so easily repeatable. And I think there needs to be a lot of analysis done to determine whether this repair-based approach is the right approach to tackle Rowhammer errors, or maybe it simply isn't possible to profile so easily, and we do need some other runtime mechanism that provides stronger correction to back it up.
Oh, great. That sounds like an exciting future work for after HARP is finally published in Micro. Thanks a lot, Minesh.
Thank you, Geraldo.
Let's see if we have questions on YouTube. Okay, we have some few questions on YouTube here. So first, this question is a slightly non-technical question according to the author of the question. Will it be feasible to get the manufacturers to include ECC bypass paths, given that it may help people to reverse engineer the ECCs? It's a great question, actually. That is quite a dream for the next.
It's just a wonderful question. Thank you for asking. Yeah, I think not only do we believe that that's possible, we hope that that occurs. I want to forward to the slide where I described the bypass path a little bit, just to talk a little more about that. So, yeah, goodness, okay, here we go. Nope, sorry, wrong slide. I know I illustrated this at some point. Okay, here we go. So there are several reasons that we expect this should be quite easy. So first, there are several works, both from academia and industry, that propose a very similar bypass path that, internally either reads out the full ECC code word, potentially across multiple data transfers, or just the data bits across a single transfer. And these works sort of analyze the costs and benefits of that approach, and they conclude that it is very low cost and simple to implement. And a second reason is that we suspect that a similar scheme already exists for testing purposes, because we've seen evidence in other devices that when there's an integrated ECC scheme, oftentimes it's useful to bypass that for manufacturers' own testing to sort of figure out what's going on and debug issues. And so in that case, having this be integrated into the commodity DRAM chips would simply be a matter of exposing this to the user. So this is a bit speculative because we don't know whether these paths exist or how the manufacturers implement the logic to potentially do a bypass path. But we do believe that it's very feasible for them to consider. And given that, yes, as you said, we can already sort of reverse engineer what's happening within the memory array and what's happening with on-die ECC. So not revealing a bypass path for reasons of security or secrecy, I don't know, it's a weaker argument given that we can already sort of figure out some of this information. And given that maybe those reasons are weaker, but there are significant benefits to be had from this bypass path, from what we describe, and also other works that show better, designs where we sort of co-design on-die ECC and rank level ECC. There are a lot of benefits to be had from exposing the bypass path. So we do believe and hope that manufacturers consider doing so in the future.
Thanks, Nash. And then there is also a second question. This one is more technical. So also what kind of modifications may be required to support the mechanism, HARP? For example, to send the extra bits to do ACC bypass? Do you propose time multiplexing the bus? What would be the overheads related to that bit?
Yeah, I know that's a fantastic question. So yeah, we didn't constrain a particular implementation. So the bypass path here, we saw two primary ways we could implement this. So first, we could add a custom read command to the DRAM device where instead of doing a normal read operation, it performs a bypass read. And so all the timings would be the same as a normal read operation. It's just that the data that's returned on the DQ pins would be the raw data bits stored within the memory, as opposed to the post-correction information. And so, yeah, this requires, extending the protocol and so forth. So while doable, it may be, a little more effort. Another possibility is to enable a bypass mode, potentially through enabling mode register level configuration. So if the memory controller were able to signal the memory controller, signal the DRAM chip that, okay, maybe we're going to flip a chicken bit inside the mode registers to say that now all subsequent reads will be bypass reads. So it's in this way, no information will be needed to we wouldn't need to communicate additional information on the actual read operation. It would just be this one-time operation of enabling this mode or potentially disabling this mode later. And that's very feasible because the active profiling takes over control of the DRAM device during profiling, right? It's writing custom data patterns, it's taking exclusive control and essentially testing the DRAM chip. So it seems reasonable that it could enter this bypass mode before profiling and exit bypass mode after profiling. But in general, yes, we believe there are several ways to achieve this, and they have trade-offs that really we believe the manufacturers are the best person to answer, because depending on their design, probably one is much more easy than the other.
Thanks a lot, Minesh. We don't have any other question on YouTube. I don't know if we have questions from the Safari audience.
Okay, I guess I'll move along then.
Sounds good. Thanks.
Cool. Thanks, Geraldo. So, okay. So now I come to the last part of this talk, which is our recommendations based on all this work that we've done and some conclusions to put this together to talk about, just the general transparency of DRAM reliability characteristics. And so this is sort of ongoing thoughts, and we're happy to incorporate feedback. So our research statement that we talked about for this entire talk basically is that we can use new memory testing techniques to recover the error characteristics that on-die-ECC obfuscates. And so these new memory testing techniques that we covered are Reaper, Beer, Beep, Ein, HARP. All of this were different ways to help overcome this obfuscation and really understand error characteristics better. So now we ask the question, what if we look at the second part of this research statement in a more general sense? Right, so here we talked about on-die-ECC obfuscating error characteristics, but in a general context, there are a lot of reliability characteristics beyond those that on-die-ECC obfuscates. So we're going to talk about that here in our recommendations. And in this part of the talk, we deal with the general problem of lack of transparency into DRAM reliability characteristics. And this begins dealing with the interface between the DRAM chip and the processor. So I'm going to start with a quick overview of a summary of our recommendations here. So our motivations here is that there is significant opportunity to be had in terms of system level metrics, such as performance and energy, by incorporating DRAM optimizations, for example, by reducing refresh rates or improving DRAM access latency and so forth. The problem is that adopting these proposals requires making assumptions about DRAM reliability. And these assumptions, for example, include error models as to how errors will manifest when we change certain operating timings, testing best practices, such as data patterns and algorithms that we talked about. And so system designers often have to generalize or infer this information from limited reverse engineering studies in order to adopt the mechanisms themselves. And so our vision is that system designers should not need to make these assumptions, or at the very least, they should make more concrete assumptions than assuming everything. And so we talk about our vision in the context of 3 different case studies. The first is DRAM refresh overheads. The second is improving DRAM access latency. And the third is mitigating Brohammer. And in each of these cases, we discuss the assumptions that underlie the proposals. And then we argue that these assumptions discourage adoption of the proposals themselves. And so based on these case studies, our recommendations are a 2-step approach towards alleviating the need for these kinds of assumptions without requiring DRAM hardware changes. And so in the short term, we ask to provide industry-validated guidelines for basic reliability characteristics that the system designers can typically already infer today, just not in an industry-validated capacity. And in the long term, we argue for changes to DRAM standards in order to promote transparency of consumer visible reliability characteristics going forward. Okay, so I'll start with some of our observations and motivation for making these arguments. So today, modern systems have very diverse targets across all of these system level metrics. Yet we're using one-size-fits-all commodity DRAM, which is very cost-effective, but it can be suboptimal for achieving these varied system design goals. Now here, I refer back to the separation of concerns slide that I presented in the introduction. In theory, this separation of concerns allows each group to do what they do best, which is to solve their own problems. And we find that many examples of these types of improvements exist. And so here I'm going to itemize a few of them. So to improve upon some characteristic, processor designers can integrate some mechanism. So for example, to improve performance, energy, and power, processor designers can exploit expendable operating timing margins. And this includes margins in things like access and refresh timings, and even operating voltage and temperature. To improve reliability, processor designers can protect against various failure modes by, for example, including system-level error mitigation mechanisms, or doing detailed qualification and validation studies of the DRAM that they integrate into their products. And even to improve security, processor designers can implement system-level defenses against potential attack vectors such as row hammer and cold boot attacks. Now, unfortunately, all of these rely on unstandardized aspects of DRAM reliability characteristics. So while processor designers can theoretically implement them, there are certain barriers to adoption in needing to make these assumptions. And so we'll talk about that in the context of 3 case studies next. So the 3 case studies deal with, first, reducing DRAM access overheads. And so we'll start there. So as we saw earlier in this talk, most DRAM cells actually do not require frequent refreshing. And so this cartoon illustrates the concept intuitively. So cell data retention times vary significantly across different cells. And there's typically a wide distribution of these owing to process variation between cells, between different chips, and so forth. However, commodity DRAM uses a highly conservative default refresh rate that is well below what most cells require. And so this means that there is significant margin in refresh timings for most chips. Therefore, there's significant opportunity for improving system performance and energy, and prior work show numbers ranging into the double digits for power and performance gains. And so let's take a look at a couple of approaches for reducing refresh overhead. So here I've reproduced the diagram from the previous slide. And so the first approach deals with eliminating the margin to operate at a 0 margin refresh rate for each chip. And so we move the conservative default refresh rate to a new refresh rate, R1. And this R1 exploits the available margin to reduce essentially unnecessary refreshing. The second approach simply reduces the refresh rate to some value R2 and mitigates any errors that occur at the new operating conditions. Now, this even more aggressively reduces unnecessary refresh operations, but as a consequence may need to deal with errors. And so the case for R1 is that we need to identify this new 0 margin refresh rate. And for R2, we need to identify the retention weak cells at the particular operating point R2. Unfortunately, both of these require making assumptions about error characteristics and/or testing. So let's look at why these sorts of assumptions are necessary. So we start with a set of desired reliability characteristics, such as worst case error rates, lists of weak cells, or 0 margin timings. And this is all information that we want to know in order to implement the mitigations that we described previously. Now, these are not provided to us by manufacturers. So in order to determine these, we use raw data from test results, such as detailed error rates or empirical error distributions. And these can come from experimental studies on real devices and so forth. However, these studies are also not provided by manufacturers. And so to obtain these results, we use a test methodology, which includes information such as worst case data patterns and best practice testing algorithms. Unfortunately, this information is also not provided by manufacturers, so we have to determine the testing methodology ourselves. And we do so based on basic chip design properties that themselves are also not provided. And so all of this together leads to assumptions built on assumptions. And so we may also make use of error models to predict the characteristics that we need. But we note that these error models themselves depend on similar assumptions about chip design properties or empirical test results that are used to create the models in the first place. And so in short, it becomes necessary to know or assume various reliability-related information in order to determine the necessary information to successfully reduce unnecessary DRAM refresh operations. And so looking at this at a more high level, this is a very messy situation where the information we need to know depends on a sequence of assumptions. And so we refer to this problem as a chain of assumptions, where each step builds on the information of the previous step, and potentially everything within the chain is assumed. Unfortunately, we observe that none or very little of this information is transparent today. And this makes sense because we are developing a methodology to operate outside of specifications. However, the need for assumptions and the need for this chain of assumptions discourages innovation and practical adoption of ideas such as reducing unnecessary refresh operations. And in that sense, it's a very real problem today. And so let's see how we can potentially obtain the necessary information today. So prior works can and do infer this information through reverse engineering and characterization studies. And especially the prior works that provide proofs of concept for these studies perform the necessary characterization experiments to figure out what they need to know. However, doing this has several limitations. So first, it's limited to the set of studied chips, and to determine the information for any other chips requires repeating the experiments, including chips that the system designer may not know that is actually used with their product, right? Because if the consumer can mix and match chips arbitrarily, the set of chips that need to be tested is, in theory, practically infinite. Second, the information that the system designer obtains through their experimental studies can potentially be inaccurate if the underlying assumptions are either flawed or mistaken, or there is some other problem with those assumptions. And third, we observe that this process can be inefficient in cases where manufacturers can trivially provide this information. For example, simple design details that are possible but potentially laborious for the system designer to reverse engineer. Therefore, we argue that access to reliable information can be a serious barrier to adopting refresh optimizations today. Now, let's take a look at improving DRAM access latency. So, excuse me, that is animation out of order. But here we have a very similar picture to that of DRAM refresh. However, this time the conservative standard DRAM latency is higher than we would like it to be. And so prior works show that we can exploit this margin or the variation, or potentially both, to significantly improve performance, again, potentially by double digits, using similar approaches to what we did with refresh. So this means that we can reduce access timings by identifying zero margin operating points, or by identifying weak cells that aggressively reduce timings. But unfortunately, this comes right back to our chain of assumptions and requires a similar process as to what was necessary for improving DRAM refresh overheads. So finally, let's discuss assumptions that arise when designing rowhammer defenses. So rowhammer is a read-to-serve vulnerability that depends on the physical organization of memory rows. So here we show some example rows that are physically next to each other. And so when an aggressor row is repeatedly accessed, nearby victim rows potentially experience errors. And so significant work has shown that rowhammer is a system-level security threat that can be exploited to mount attacks. Unfortunately, in DRAM defenses that are used to prevent rowhammer today fail to do so. And so a system designer who is interested in security may need to consider their own defense mechanisms. For example, in the software or within the memory controller, because such a solution would be trustworthy and then within the designer's own purview and control. So here's a categorization of defense mechanisms that has been proposed by prior work. Unfortunately, we observe that these works all collectively depend on knowing exactly how vulnerable a chip is to rowhammer. And this is usually quantified by parameters such as maximum activation count, or HC first, which stands for hammer count. And so as with identifying zero margin timings, these values are not provided by manufacturers and must be determined by testing, which circles right back to our chain of assumptions that we've been talking about. So now that we've examined these use cases, let's talk about how we can potentially improve transparency. So again, we refer back to the separation of concerns. Commodity DRAM is the commodity DRAM specifications, do not address general reliability characteristics by design. This is because the separation of concerns is a long-standing thing, and it defines the goals sort of for the entire industry. In particular, commodity DRAM is designed for a fixed, cost-optimized operating point, and efforts to change that operating point are essentially going counter to the specifications. And so it's somewhat understandable that we don't have access to this information today. Unfortunately, we observe that the opportunity cost of maintaining this status quo is increasing. And this is because technology scaling exacerbates problems like rowhammer, refresh, access latency. And we have seen many proposals that try to leverage this opportunity to improve system-level metrics. Now, we believe that the very existence of these proposals to improve upon commodity DRAM operating points indicates interest in having more flexible commodity DRAM. However, current DRAM specifications do not provide the transparency and therefore the opportunity to easily adopt them. Therefore, we propose to revisit DRAM specifications to improve information transparency. And so now, referring back to our chain of assumptions, our key idea is to break the chain at any point possible. This is because knowing information at any link in the chain with some level of certainty enables reliably determine the following links. Because these assumptions are built upon each other, if any one of them is no longer an assumption, the following assumptions are no longer so, let's say, based on assumptions, they're based on some concrete evidence. And in other words, any information at all really is useful towards the end goal of having flexible DRAM operation. So finally, let's take a look at our recommendations for improving transparency going forward. So we believe that that information at any level can be helpful. So ideally, we'd have full transparency into everything, and so no assumptions are necessary at all. Realistically, we recognize that some information is much easier to provide than others for practicality reasons or reasons of secrecy that the manufacturers may have. And so the question naturally arises, which information should be provided? Here we review a few possibilities, but we leave system designers and DRAM manufacturers to really decide what is most feasible and most practical to release. So we start by looking at the root of the chain of assumptions, which is chip design properties. Examples of this information include things like the true and anti-cell layout, which we previously saw is very integral to data retention errors. The on-die ECC implementation, which we've been working on throughout this talk. The bus to internal address mapping, which is very important for rowhammer defense. Substructure organization, which is useful for some access latency reductions. And circuit level modeling parameters, which are generally useful for just understanding errors and potentially developing mechanisms based on these models. Now, chip design properties is essentially the most general and flexible category because it does not place limitations on what sort of studies can be performed with this information. Now, we note that most, if not all of this information can be reverse engineered with existing techniques. And so revealing this information at least is not a problem from the perspective of having this information be obfuscated or secretive. The next level that we consider is the second link in the chain, which is test methodologies. Examples of test methodologies include worst case data patterns, environmental parameters such as temperature, voltage, and their effects on testing, potentially testing algorithms. And so we summarize this by saying testing best practices or recommendations or guidelines. And this is ideally what we'd like to see in an official capacity. So having this information can streamline testing and prevents the tester from coming to incorrect conclusions, either based on limited testing methodologies or improperly conducted studies or flaws in the assumptions in general. We note that this could potentially be similar to JEDEC testing guidelines that are provided for semiconductor testing or even NAND flash memory in some of the official JEDEC documents. Now we note that this approach is moderately flexible. It's not as flexible as having chip design properties because it's specific to the particular tests provided, but it still allows the tester to use the tests for whichever purpose they want to. The final piece of the final level of the chain that we consider is sort of the error models and test results and the end reliability characteristics we're looking for. So examples here vary, but we have examples such as providing statistical models plus the necessary parameters for particular devices, having raw parameter values themselves. For example, directly providing this HC first that describes the rowhammer vulnerability of a chip. Potentially even providing fine granularity operating timings for different devices, such as, for example, row level refresh rates or word level access timings. We note that this approach is the least flexible because it's very specific to a particular use case. However, it potentially has the upside that it allows system designers to directly tune their mechanisms for taking advantage of these quantities without having to worry about assumptions or figuring them out themselves. And so we conclude with a two-step plan for transparency in order to talk about how to release this information. And so we believe there is no need to change DRAM hardware design practices. We would simply like to have the information available for system designers to use to make informed decisions in the course of their work. And so our two different steps are that in the short run, we would like to be able to convey basic information from the DRAM manufacturers or essentially from the industry to system designers. And they can provide whatever information they're able to do so, and anything that makes it practical for the system designers to adopt these flexible DRAM optimizations. And the second is, in the long term, we hope to make modifications to the DRAM standards, which incorporate this transparency into the specifications in a way that consumer visible reliability characteristics are accounted for, and the DRAM standards themselves allow for more flexibly operating commodity DRAM and more easily allowing it to be adapted to system-specific purposes. And so that concludes my talk, actually. And so I think that at this point, this is the last slide I have, and it summarizes the different contributions that we talked about. And I'm happy to take questions about, the conclusions, the recommendations, or anything. Thank you.
Thank you so much, Minesh. That was an excellent talk. I have two questions for you. The first one puts you on the spot. So you provide all of those recommendations, and I understand that they have a bunch of trade-offs related to that. But if you, as a system designer, have to choose one recommendation to give to the RAM vendors, which one would choose based on whatever metric that you consider important?
Yeah, that's a very open-ended question. So I think in terms of recommendation, I want to move to a slide that I presented here, where we talked about okay, this slide. So here, just to give a recap of the slide, essentially the message here was that the DRAM standards currently don't address these reliability characteristics or the flexibility of different operating points because of a long-standing history of not needing to, and the fact that commodity DRAM simply isn't, that this isn't the operating target for commodity DRAM. As a recommendation, I think this is the single most important thing to highlight out of all the recommendations that I provided, because the message here is that we should really be thinking differently about these specifications, right? Because if all of this opportunity cost exists, these problems are getting worse, people have already come up with ways to begin addressing these problems. The only thing holding it back is, I shouldn't say the only thing, but one of the largest things holding it back is the status quo of maintaining the current DRAM interface. And it comes with a lot of challenges. Adjusting the interface comes with a bunch of challenges, right? It requires potentially assuming different responsibilities on the sides of DRAM manufacturers and consumers, potentially things that have not been explored before. But I do believe that these can be very valuable going forward, not only because they enable optimizations such as those that we talked about, but also just in general providing a more flexible DRAM substrate that system designers can use to better fulfill system-specific needs. So yeah, just to summarize, I very much think rethinking the interface is the single most important piece.
Thanks a lot, Minesh. I think it makes a lot of sense. And that leads to my second question. That is more like a comment than a question. That there are a lot of proposals that tries to accelerate a bunch of data-intensive applications by rethinking DRAM organization or DRAM interface, by reducing latency, or proposing solutions as processing using memory that quite also take a bunch of assumptions to work right. Like, for example, we have ambit or row clone that requires a specific organization of the subarrays and organization of the design of the system amplifiers that we usually rely on JDEX standards to give us some information of what's happening behind the scenes over there in the DRAM array, but they are not necessarily always true because we actually don't know the core design of the array itself. So my question is, do you think also that being more transparent could enable also to the DRAM design to be more efficient and to solve the memory wall problem via pick your favorite solution over there, processing memory or whatever?
Yeah, I understand the general gist of your question, I think. So the first thing I want to say is that in the set of recommendations that I discussed here, we very much focused on not touching the internals of the DRAM, right? It was all very much from the perspective of the system designer and the processor and things that they can do to adapt commodity DRAM as it stands today to fulfill their own needs. Systems that you're describing, potentially, like ambit and so forth, to officially support them would likely require modifications to the actual DRAM device, right? Like, so there have been proposals like this compute DRAM work that show that you can do potentially a limited amount of this functionality using commodity devices. And in that sense, for those kind of proposals, I think improved transparency very much would help, because they're designed around exploiting behavior of commodity devices that isn't known, but is somehow inferred or reverse engineered or just observed from studies in general. But knowing exactly how that operation is occurring could allow not only making that operation more reliable, but potentially developing other similar operations. And we've sort of seen this in a lot of proposals recently with these proposals that generate random numbers or implement these puffs, these probabilistically, or I forgot what puff stands for. The fingerprinting methodology, right? But yeah, so these mechanisms are somehow based on characteristics of the technology that are not provided in an official capacity, but they are relied upon in order to make the proposal work. And so for these types of proposals, I very much think exposing more information or providing transparency is one way to enable more of them and help those proposals work. In the context of more invasive changes that maybe change how the architecture of DRAM works in order to enable things like in DRAM processing or potentially even customizations for near DRAM processing, I think it varies very much on the proposal itself. Because if we're talking about changes to the core DRAM array architectures, probably those changes are going to be made by the DRAM manufacturers themselves, in which case they don't necessarily need transparency for themselves, right? And exposing this information can have the previous benefits that we discussed, like maybe those improvements or those changes can allow system designers to exploit new functionality, but it doesn't necessarily help the adoption of the processing memory system itself. So I want to say it very much depends on the level at which we're adopting these proposals. And for the perspective of the consumer solving their own problems, I believe transparency is very, very helpful. For a joint co-design of the DRAM, the processor, or maybe just changes to DRAM itself, I think it's hard to say right now.
Completely agree. Thanks so much, Minesh. So we don't have any other question on YouTube. Do we have any other question from Safari members?
Maybe I'll ask a few questions. Thanks, Minesh. This was a great seminar so far. It's a bit long, of course. So maybe at some point it's time to do another seminar on especially the later parts discussing these recommendations, because I think they're quite important. And certainly the DRAM interface requires some rethinking, and I think your recommendations are cutting to the heart of the problem. I have some questions related to that. First, I have a comment. One thing that you did not mention, but it may be in your head, is voltage. Voltage is also another parameter that can be controlled if you have a better interface to control it, right?
Yeah, yeah, I think that's true. And whether that's from the perspective of exploiting expendable margins in voltage, which I guess a couple of prior works have shown, that Kevin Cheng's work that you referenced previously, or even using the if there's some side effect of changing the voltage, say, like maybe changing the voltage can cause the core array to operate differently with some properties that are desirable, right? Maybe it helps change the retention times of cells, or changes the behavior of one of the error mechanisms that we care about. Yeah, I agree that that is definitely another independent variable that the system designer has control over, but doesn't necessarily know how it's actually affecting the DRAM device. And transparency in that respect, I think, goes hand in hand with the other aspects that we talked about here. I do agree with you. Yeah,
certainly. That brings another comment that I had that bothers me a little bit, and that's the issue of power management of DRAM today. I mean, certainly there's an interface to help power management, right, in DRAM chips. Is that something? I know you had a lot of ideas, certainly, but is the change? Is an interface like that something that would be useful for these other parameters as well? Maybe I didn't phrase it very well, but
Okay.
memory controller, for example, can manage power modes of DRAM chips, right? You can put it into self-refresh, even though they're coarse-grained right now. Maybe you need more fine-grained power modes. But certainly there's an interface to enable power management, and you know how the chip would behave if you put it into a particular mode. You would guess the power consumption. There are power calculators that manufacturers provide as well. So is it something that you're envisioning for these other parameters too, like latency, voltage, I don't know, maybe row hammer?
Yeah, I think that your point is very interesting, and I don't think we've given that much thought yet, actually. But yeah, so it brings up the general theme of, in these power management interfaces that you described, somehow the memory controller has full control over the state of everything, right? And so it's dictating that, okay, regardless of what needs to happen, right now I want this power mode. And so maybe you enter self-refresh and you do that at the granularity that you're able to. But we don't necessarily have the same level of interface for all these other parameters, right? And I think that's what I understand from your question. That, for example, for access timings, we have a fixed set of access timings, and if we play around with those, it's in an undefined way. Whereas with the power interfaces, it is in a very defined way, even if it's somewhat discretized, maybe.
Yeah, exactly.
Yeah, I think that's a very interesting point, because it's also going beyond the sort of just transparency, right? So now it's not only transparency, because you would want to know how to make use of that transparency to, I guess at some level make best use of it, right? So I need to understand the effects of changing these latencies, and then also have the ability to change them in a reliable way, or in a specified way almost. I think we haven't thought about that too much. I don't have any great discussion points at this moment, but I think we'll definitely think about it.
Sure. Yeah. I think this would be something to think about, because this interface already exists, whereas it didn't exist some time ago, right? A power management interface was added, I guess, relatively recently in the history of DRAM. And the question is, of course, is an evolution like that desirable for other parameters? Perhaps yes, but if it's a very rigid interface, then that may not also be nice, right? Because many people complain about the power management modes and how coarse-grained they are today.
Certainly. Yeah. If nothing else, it could potentially be a stepping stone towards something just more general.
Yeah, potentially, although power management mechanisms have not improved a lot, and the interface has not improved a lot over the course of 2 decades in DRAM. Yeah, once you set it, it just gets set in stone almost in DRAM. Okay, and there are reasons for it, some of which is, certainly what you mentioned is it's limiting innovation, it's limiting overall system design improvements, as you mentioned. So it's not necessarily a good thing that this interface gets set in stone, almost set in stone, let's say. I have another question that's related to this, unless you have a comment on what I said.
Yeah, I was going to add one thing, actually. I think one thing we were thinking of is, in terms of what you described, the evolution of the specifications. One point that I remember we were discussing a lot was that, as the specifications continue to evolve to meet, I guess, systems needs, in theory, they should account for, I guess, everything that consumers might want to do and everything that manufacturers might want to do, and somehow come to a happy medium in between. And I guess that paints a very idyllic picture of what should be happening. But the fact that we observe all of these proposals that can't really be adopted based on the current interface sort of hints towards the fact that maybe these proposals the specifications have been aging without sufficient attention to the flexibility. And now all of this is sort of coming to a head, where we have all of these things that are difficult to do because there's an artificial roadblock. And it could have potentially been addressed if, flexibility was considered before or thought about. But now these challenges are mounting, and considering flexibility becomes, more and more of a relevant problem. So I feel like we're headed in this direction. I think it warrants a little more thought.
Yeah, I absolutely agree with that. I think, I think the interface has also exacerbated some of the scaling issues, like row hammer. If the interface was flexible, perhaps row hammer could have been more easily contained within a DRAM chip with that's co-designed with a controller inside, right? Without requiring, if such a controller didn't require to obey a rigid interface, it could have done more inside the DRAM chip. But yeah, that's something we've been arguing for some time also. Okay, so a related question, I think, to these recommendations. A lot of these require the manufacturer to reveal information, right? And manufacturers are already claiming that they're extremely cost constrained. Maybe that's a myopic view on their part. Maybe they're very much stuck in a particular business model, but that's how it is right now. They're claiming they're very cost constrained, and revealing information requires more work, and more work is more cost because they need to test more, and probably testing more is the biggest disadvantage of revealing more information, because they need to be corrected when they reveal information also, otherwise it won't work, right? So the question is, how likely is it that manufacturers will do more testing to reveal more information? And maybe put another way, what is in it for the manufacturers? Clearly there are system level benefits, but if you're a selfish manufacturer, what is in it for you?
Excuse me. Yeah, I quite like that question. And so I think this is one of the biggest reasons that we weren't trying to set a hard line and say, this is the information that needs to be revealed, right? Because it's sort of not clear to us exactly what the trade-offs are for each piece of information that we might ask for. And so here we were saying that we believe that information at any level is helpful. And I think that very much is true, because whatever we can work with is beneficial from the perspective of the system designer. And so ideally, this process can start out by manufacturers revealing information that's very low overhead for them. And I understand that, yeah, certain information might require extensive testing or additional work or guarantees or something from the manufacturers that, as you said, increases costs or liability. And maybe those pieces of information are not the first things to be revealed. But I think there are other pieces of information that there's very few reasons tangibly to keep it hidden. For example, I want to argue that on-die ECC is such a piece of information, right? We have all these techniques to sort of look into the implementation and figure out what's going on, and revealing, for example, something as simple as the H matrix for a given on-die ECC chip, or a chip that uses on-die ECC. This should not require additional effort in terms of testing or anything. It's simply revealing a design detail. And there are good reasons to hide design details if somehow they affect, a potentially market competitiveness or enable something else. But we don't believe that those reasons apply so much to something like on-die ECC, because it's a simple detail that can already be figured out today. And from that perspective, I can't use it for some sort of competitive advantage play because it's readily known. It's public knowledge in some sense. So things like design details, I think, do not require additional testing to reveal, but they do allow the system designer to flexibly do whatever they want with it. And at that point, I guess the argument of cost moves from needing to figure out something from the manufacturer's end to figuring out if there are liability concerns or things like this, promises that they're making that they may need to keep later on, which maybe put them in an uncomfortable spot. I think those are very hard for us to evaluate. From the outside perspective, it seems like something like on-die ECC is not too big a deal, but if there are underlying reasons, then I think that's something that at the very least needs to be brought up and discussed, if not, revealed. Does that make sense? I think that's sort of the perspective that we're taking here.
Yeah, I think it makes sense. Certainly, lower effort information or lower cost information is easier to reveal unless there are other concerns, like you mentioned, like liability. But that makes sense. I think you need to start step by step for sure. I guess, of course, then that brings up the question, on-die ECC, I think, is a good example if you can reveal that information. How many other such pieces of information are there that are low effort?
This is a fantastic question, right? So in this one slide here, I think we itemized a few design details. I'd just like to go back to that. So yeah, so here we have things like the true anti-cell layout on the ECC implementation, the address mappings. At the high level, some of these are very easy to reveal, right? So let's say, for example, the true anti-cell layout. Many works have shown that it's very easy to figure that out just by doing a long-term retention experiment. And so this is a design detail of the manufacturers know how they built their device, and they could describe this for each model of their chip, and that saves the system manufacturer from having to figure out some testing methodology that works for all devices and so forth. But there are potentially complexities hidden in there. For example, rows and columns that are used for row and column sparing might use a different true and anti-cell layout, in which case revealing this would require additionally revealing other information. And something like the row and column sparing is, I guess a lot of works have discussed that this is very much tied to yield and other manufacturing concerns, and we don't want to reveal that information. So now potentially we're asking for a partial revealing, right? So you partially reveal the true and anti-cell layout as the general design, but not how it works for every single piece of the design, i.e. every single spare row and column. And I think the same arguments can be applied to other things like the bus to internal address mapping. Like we can give the overall row organization, but the organization for rows that have been remapped, that potentially is more of a hairy concern. But it would also be nice to know that in order to build an effective row hemorrhage prevention mechanism. So I think there are lots of nuances here that while at first the information seems harmless even, digging into detail, there are potentially consequences of revealing that information. And so I don't know how to answer, like, what is the simplest thing to reveal? Like on ECC is a good example from the studies we've seen, but some of these other examples come with hidden costs potentially. So I think that's sort of my stance on the issue at this point.
Yeah, absolutely. I agree. I think if you go into the details of all of these, I think there are interesting issues to consider. Yeah, but I agree overall that some of the information you write over here is relatively easy to reveal compared to some others, right?
Right.
Like latency characteristics or voltage characteristics may be harder to reveal because that requires extensive testing.
Right. Yeah.
Yeah.
So yeah, in that sense, yes, we argue that yes, if the testing is of interest to a system designer, ideally we should enable them to do the testing, and then that's the best case, I suppose.
Sure. Yeah. Okay, I had some other question related to this. Yeah, I think maybe more of a comment than a question. And part of the reason I think some of this information is not revealed is because the interface also doesn't allow it as much. And also, going back to the cost, it's probably all about a cost-oriented mindset from the manufacturer's perspective. Maybe the business model also needs to change a little bit. Clearly, that's something that we're not going to tackle here, but maybe if the benefits of revealing this information in terms of scaling the DRAM into the future can be proven, it will be easier to reveal this information and add more cost to the DRAM, right? So I guess it's always easy to reveal more information if someone pays for it.
Right. So the question is whether it's worth it to do so.
Exactly. Yeah. Exactly. Yeah. Okay.
Oh, can I add a point, Hunter?
Yeah. Sure. Go ahead.
So there are also custom DRAM organizations, right? So I don't know, like smaller manufacturers who produce special purpose devices and so forth. And I think one argument may be that if some of these proposals can be demonstrated there and the benefits clearly seen, that could very much help motivate the sort of critical mass of the commodity market. Is that something that, I don't know, you believe is already going on today, or is it something that needs to happen in the future?
Yeah, that's a good question. I think, yeah, I'm not sure if it's really going on. Certainly, there are some custom things that are added, especially small manufacturers can do that more easily. But if you look at the large manufacturers, they're mostly dominated by essentially cost, right? And the markets, how large is the market for a particular optimization that you want to add, or particular information that you want to provide. If the market is not large enough, then they usually dismiss anything new, let's say. Let's put it that way. And I think that's, yeah, there's a danger here. And that's because DRAM has become too much of a commodity, in my opinion. Maybe we should really pull back and make it less of a commodity and make it something more valuable, right? Given the importance that DRAM and memory plays in the system. But again, that's not easy also. I feel like that's why when I give lectures on this topic, I talk a lot about mindset. For example, we're in this mindset where people, everybody, including the manufacturers as well as system designers, think of DRAM as a commodity. Even though system designers want more from DRAM, they're not willing to pay for it in general, because they think of this as a commodity, right? It should come for free, almost free, let's say. And I think if we really want to improve the overall system, maybe we should take a step back from that mindset and think of DRAM's role in the entire system: performance, energy, reliability, security, everything, and maybe place the right value in terms of cost and in terms of the money you pay for it, basically, in the entire system. That's my feeling.
I think it makes sense. Yeah.
Yeah, but of course that's also hard to do. I think everything you mentioned, these small steps will help, but at some point I think there needs to be a big mindset. That's why I think things like processing in memory, things that can disrupt how DRAM evolves, can be very beneficial in changing the mindset, right? Processing in memory is one example, or interfaces that are more flexible, like this open memory interface, or I guess they have the Compute Express link, more disaggregated interfaces that can enable more internal operations inside DRAM can help, right? But then again, there's the other question, right? You may have controllers close to DRAM, but those controllers may not be exposed to the system. As a result, overall system may not be improved, right?
Sure, you've pushed the problem to a different piece.
Exactly. So I think in the end, you really need to optimize the entire system if you want to get the maximum benefits. But like the processor, controller, and DRAM at the same time. Like even in flash memory, for example, we have nice scaling, let's say, because you can co-design the controller and the flash chip together nicely. Many manufacturers do that. But system designers still want more control over flash memory. They complain about lack of control over the flash controller, let's say. So ideally, if you really want to optimize everything, you really want to design the processor, accelerator, controller, and memory at the same time. But that's of course not easy to do, and the application. Okay, maybe certainly this is fun to talk about, but I don't want to take much longer since it's already been a long seminar. So unless you have more, maybe I'll mention one thing related to your work that I didn't really, that I think came across, especially for Beer and HARP, certainly not for HARP. So all of these works, Ein, Beer, and HARP, are completely open source, right? People can find it online. Maybe HARP is not yet available, but it will be available. Actually, that's already available, right?
Yeah, I think we'll be pushing some updates, but yeah, it is available.
Yeah, I think that's good to mention. And I think open sourcing all the works probably helps toward the recommendation directions that you have mentioned. Because if everything is open, then it's easier to certainly evaluate the benefits of these works, and also potentially convince people to actually expose more information, because the information is already openly obtainable anyway, right, with the reverse engineering.
Yeah, Yeah, I agree with that point. Yes, it's at least the methodology and the tools are readily available for you to adopt them if you care about the issue and have interest. So, yeah.
Okay, cool. Let me see. I think there's one more question on YouTube, but I guess before Geraldo asks it, I will ask one question, one technical question on HARP. I didn't get a chance to ask it when you presented it. And that question is, how strong should the secondary ECC be?
So, yeah, let me just go back to that slide so that we have some context. But yeah, the short answer is that it should be able to correct the indirect errors, right? So that we ensure they don't propagate into the rest of the system. So in that sense, it should be as strong or greater than the on-die ECC. And this comes with a caveat because it needs to be at the granularity of the ECC word that on-die ECC uses, right? So if on-die ECC is operating with, say, a 128-bit word, then say it's a single error correcting code within those 128 bits, then secondary ECC needs to ensure that it has at least single error correcting capability within each on-die ECC word. So naively applying a single error correcting secondary ECC will not work, right? You have to make sure that the mapping is set up such that the error correction strength is applied per on-die ECC word, because that's the granularity at which indirect errors can occur. And so that's the point I was trying to make here with aligning the on-die ECC and secondary ECC words. We do discuss this in the paper a lot more. It's a really general design problem that even other proposals that try to co-design on-die ECC and secondary ECC need to deal with, because fundamentally, any error behavior that on-die ECC introduces is exhibited independently for every on-die ECC word. And it's, yeah, there's endless possibilities there. And I think the short answer is yes, that the correction capability is the same or greater per on-die ECC word.
Then I think, if I understand what you're saying, the flexibility of secondary ECC is very much dependent on what's implemented in the on-die ECC, right?
Yeah, I believe that's a correct statement, yes. So if a different memory chip comes along with a different ECC word size or correction capability, the secondary ECC will sort of also need to change. But I think I just want to add that I think that's also the case for today's memory organizations, right? Like, let's consider a rank level ECC system. In order to provide, say, chip kill guarantees, you need a specific chip organization. And if you don't have that organization, you don't provide the guarantee that you're looking for. So it is a limitation, but I don't think it's anything too new.
Yeah, I agree with that. I guess I have not considered this as much, but one related question is, can you make secondary ECC software based?
So I think Geraldo's question that he asked was actually asking about the same thing.
Okay.
And in that sense, yeah, we don't necessarily need secondary ECC for reactive profiling. Any technique that can identify these remaining indirect errors safely is fair game. And so if it, at the example you gave of software, if we did have, say, task replication, and it had a way to identify exactly which errors occurred when an error does occur, if that software-based mechanism can give feedback to the repair mechanism to repair those identified bits, I think there's no longer a need for secondary ECC because we have a different mechanism performing that function. Yeah, I think that's not limited to software even. There's many ways, yeah, I mean, it's whatever your imagination allows you to do.
Yeah, exactly. I think, yeah, the design space is relatively large in that case.
Right.
Okay, cool. I don't have any other questions. Thanks, Minesh. I'll let Geraldo ask the YouTube question then.
Thanks, Onur.
Thanks, Onur. The YouTube question is actually quite nice. So it's related to open source. So do you think that open source DRAM project similar to or inspired by the RISC-V open source project would be a good idea to solve those problems that we have been discussing over here? So I want to preface this by saying that
open source is wonderful, and I think yes, it is definitely something to work towards. But as far as alleviating the challenges that we have here, I'm not entirely certain, because something like RISC-V is very helpful for designers who want to say add their own processor, right? They have a fully viable design to go and integrate, and it can be state of the art, and you can rely on it to just be a good design. And so if we had something similar for DRAM, now we would be asking, instead of buying commodity DRAM, the system designer might be like, maybe we can use this open source DRAM and integrate that into our product. And it's a better replacement for using a commodity DRAM device. And I think that's difficult to conclude anything from, because for one, the DRAM process technology is typically very different from the standard CMOS process technology. It's optimized for different things, like, for example, low leakage currents. And this means that fabricating the same thing in the system designer's design might not lead to as optimal a DRAM as can be produced with a commodity part. There are alternatives, of course, like we could have a more open source embedded DRAM type initiative. But I think my point is that there are advantages to the DRAM process technology being highly optimized for the commodity devices. And if we have an open source design, presumably it's no longer optimized for a particular process or for a particular use case, or if it is, then aspects of it might still remain proprietary. I don't know how to make conclusions about that. But I don't think it immediately solves the problem of the system designer wanting to make the best of DRAM, let's say. I think it adds another design alternative, which, if for their system adopting this open source DRAM design with any potential disadvantages it comes with, is actually a better trade-off because it allows them to use one of these system level mechanisms, then I think that sounds amazing. But I don't think it's a general solution to the problem.
Thanks, Minesh. I totally agree. And we don't have any other question on YouTube. So if there is no other question from the Safari audience, I think we are done for today. Let's wait to 1 more minute to see if anyone has any further question. Apparently not. Minesh, thank you so much for the excellent talk. Thanks everyone for joining. And I guess we're done for today.
And thank you, Geraldo, for moderating.
Thank you. Bye-bye.